Pipe Dream Part 3. The Living Underworld. MXTM aka Pirate 1 or VJ Tsunami X. July 9, 2026. Chapter 1, Rivers Beneath the Jungle. The Yucatan Peninsula has no rivers. This is the first fact a surface world hydrologist notes and the last fact a surface world hydrologist understands. No rivers means no drainage. No drainage means the rainfall that falls on the jungle, and the Yucatan's wet season delivers it in quantities that would constitute flooding events in any temperate geography, disappears. The jungle absorbs some. The rest vanishes into the ground and does not reappear. No streams form. No channels cut the limestone surface. No delta deposits at the coast from any significant inland flow. The peninsula's surface is hydrologically inert in the sense that matters to any civilization that has ever organized itself around a river. There is no river to organize around. This is not a hydrological deficit. It is a hydrological architecture. The rainfall that enters the limestone does not stop moving. It moves downward, through the karst, the dissolution fractured, porous, honeycombed limestone that underlies the peninsula's entire surface area, finding the fracture networks that the Chicxulub impact opened 66 million years ago and that 66 million years of acidic rainwater has widened, smoothed, and organized into passages with hydraulic geometries as precise as any engineered conduit. The water moves through these passages under a hydraulic gradient. The inland water table sits higher than the coastal water table, and the difference drives flow from inland recharge zones toward the coast. The water reaches the coast. It just never sees the sky on the way. What the surface world calls the absence of rivers is the presence of a river system of a scale and continuity that has no surface world equivalent in a comparable geographic area. The mapped passages of the Yucatan's connected cave systems run for hundreds of kilometers. The unmapped passages, the ones the lithocrustaceans are boring toward, the ones the coordinating system's acoustic transceiver chains have detected at range but no bore has reached, extend the network by an order of magnitude that no definitive survey has bounded. The full extent of what flows beneath the jungle is not known. What is known is enough to build a civilization on. Pipe Dream did not install its water infrastructure. The water infrastructure was already there. The karst. Limestone dissolves. This is the property that determines everything about the Yucatan's underground. Calcium carbonate, the mineral that composes the peninsula's limestone bedrock, reacts with carbonic acid, produced when atmospheric carbon dioxide dissolves in rainwater, to form calcium bicarbonate, which is water-soluble and washes away. The reaction is slow at geological timescales, fast enough at human timescales to be measurable but not fast enough to be visible as a continuous process. What is visible is its accumulated result, passages where limestone has been removed by dissolution over millions of years, leaving voids of every dimension from hairline fractures to cathedral chambers. The Chicxulub impact's role is specific and irreplaceable in the Yucatan's karst architecture. The impact fractured the limestone in a pattern radiating from the buried crater rim, the same pattern that the cenote distribution traces across the peninsula's surface. The fractures are not uniformly distributed. They are densest at the crater rim, where the impact's energy was concentrated, and they decrease in density with distance from the rim. The densest fracture zones are the zones where dissolution has proceeded furthest, where the greatest limestone volume has been removed, where the largest cave passages have formed and where the passage networks are most extensively connected. Pipe Dream occupies this zone. Not by coincidence, the hydroprint survey that preceded the founding module's installation identified the crater rim fracture zone as the location with the highest connected passage density, the most stable hydrological regime, and the richest biological community of any surveyed area in the peninsula's cave network. The formation was chosen because the Chicxulub impact's 66 million year legacy had produced, at this specific location, the most extensively developed underground geography available to any construction program operating within the peninsula's boundaries. The impact site is not Pipe Dream's geological inheritance in a metaphorical sense. It is Pipe Dream's literal infrastructure substrate, the fractured, dissolved, connected limestone that exists because a 6-mile-wide asteroid struck this location at 15 kilometers per second. The civilization was made possible by an extinction event. This fact is in the founding charter as a statement of geological context, not as an irony. The formation does not care about irony. It offers what 66 million years of dissolution produced. Pipe Dream accepts the offer. What a passage is. The surface world's understanding of underground rivers draws from a tradition of cave exploration that is primarily vertical, a rope descent into a known entrance, a swim through known passages, a return to the surface through the same entrance. This tradition, and the cartography it produces, represents the cave system as a series of passages connecting known entry points. It does not represent the cave system as what it is, a three-dimensional fluid network occupying a significant fraction of the limestone's total volume, with no preferred entry point, no surface visible extent, and no boundary that has been mapped to its full extent at any point in the history of cave exploration in the Yucatan. A passage in the context of this network is not a tunnel in the engineering sense, a structure with a defined cross-section, a designed alignment, and a known beginning and end. It is a void whose cross-section varies along its length from hairline to hundreds of square meters, whose alignment follows the fracture networks and bedding planes that dissolution preferentially enlarged, and whose beginning and end are connected to other passages that are connected to other passages in a graph of connectivity that no complete survey has yet bounded. The river that flows through this graph is not a single channel. It is the aggregate of all flow occurring within the connected void network, flow that divides and recombines at every passage junction, that occupies the full cross-section of a passage in flood conditions and a fraction of it in dry season low flow conditions, that moves through some passages as turbulent high-velocity flow and through others as laminar barely perceptible drift. At any point in the network, what flows past is the sum of what has flowed through every upstream passage that connects to that point. At the coast, where the network discharges into the Caribbean through submarine springs called Anchialan outlets, what emerges is the aggregate of everything that entered the network through every cenote opening and every soil infiltration point across a catchment area that covers a significant fraction of the peninsula. Pipe Dream's installations occupy nodes in this network. The founding module sits at a cenote, a collapse point where the cave ceiling has failed and the passage below has become accessible from the surface. The crystal tube connections that link the founding module to adjacent cenotes run through existing passages where the passage geometry permits tube installation, and through lithocrustation bored tunnels where it does not. The civilization is not inside the network. The civilization is a part of the network, a set of inhabited nodes connected by engineered tubes running through the same passages that carry the underground rivers. This is the relationship the founding charter describes as aquaforming and the engineering doctrine implements as crystal tube connections following passage geometry rather than designed alignments. The tube is where the passage already is. The civilization is where the water already flows. The flow regime. The underground river system operates on two timescales simultaneously, the diurnal cycle of groundwater recharge from daily rainfall distribution, and the annual cycle of wet season and dry season that determines the hydraulic gradient driving flow from inland to coast. The wet season, broadly May through October in the Yucatan's climatic regime, delivers the bulk of the annual rainfall in concentrated events. Tropical convective storms produce precipitation rates that saturate the jungle canopy and the thin soil layer above the limestone within hours, after which the rainfall passes directly through the karst surface and enters the cave network as recharge. The water table rises. The hydraulic gradient steepens. Flow velocities in the passage network increase. The halocline, the boundary between the freshwater flowing inland to coast and the denser saltwater pushing upward from the Caribbean, moves. In high recharge conditions, the halocline is depressed downward by the increased freshwater pressure from above. The freshwater zone deepens. The saltwater zone's upper boundary retreats. The dry season reverses this. Rainfall drops to a fraction of wet season rates. The water table falls. The hydraulic gradient flattens. Flow velocities in the passage network decrease. The reduced freshwater pressure allows the saltwater's density advantage to push the halocline upward. The freshwater zone shallows. The saltwater zone advances. Pipe Dream's halocline management protocol is built on this annual cycle. The founding module's trial window, the minimum 12-month neutral buoyancy period before anchor commitment, was specified at 12 months precisely because 12 months is the minimum period required to observe the full halocline depth range, from its dry season high point to its wet season low point, at the founding module's location. An anchor driven at the wrong depth for the halocline's annual range places a module designed for halocline zone conditions in freshwater zone conditions for part of the year, or in saltwater zone conditions for part of the year, or, worst, at a depth where the module crosses the halocline at one seasonal extreme and does not cross it at the other, producing conditions for which no single set of material and operational specifications is correct. The digital twins halocline model is the coordinating system's most frequently updated model layer. Halocline depth is measured continuously by salinity sensors at multiple depth stations throughout the formation. The measurements feed into the digital twins hydrological model at the same update frequency that the piezoelectric network updates the structural health model, continuously, not on a schedule. The halocline is where the formation's two dominant water masses meet. Its depth is the most sensitive indicator of the formation's current hydrological state. The civilization that lives across the halocline treats its depth as a vital sign. The flow velocity regime has direct engineering consequences for every tube section installed in an active passage. A crystal tube in a passage carrying high-velocity flow in wet season conditions and low-velocity flow in dry season conditions is a tube subject to variable hydrodynamic loading. At high velocity, the flow exerts drag force on the tube's exterior surface and dynamic pressure on any cross-sectional obstruction the tube presents to the flow. At low velocity, these forces approach zero. The tube's anchor system must accommodate the peak hydrodynamic load without allowing the tube to deflect in ways that stress the crystal tube joints beyond the fast-cure polymer's compliance range. The passage geometry mitigates this problem where tube routing follows the passage's widest dimensions. A tube occupying a small fraction of a large passage cross-section presents less obstruction to flow than a tube fitted tightly into a narrow passage. The lithocrustation boring protocol for new tunnels sizes the bore cross-section to the crystal tube outer diameter plus a minimum annular clearance specified in the boring operations manual, enough clearance for the tube's anchor brackets to be secured to the tunnel wall without the tube touching the wall at any point around its circumference, reducing hydrodynamic contact forces to the tube's anchor points rather than distributing them across the tube's full exterior surface. In existing passages where the tube must route through restricted dimensions, the digital twin's hydrodynamic model calculates the peak flow velocity at the restriction point under wet season high recharge conditions and determines the anchor spacing and anchor force required to keep the tube's deflection within the joint compliance range under those conditions. If the calculation produces anchor requirements that the passage wall geology cannot support, the limestone at the restriction point too fractured to take the anchor loads the hydrodynamic conditions demand, the routing is redesigned around the restriction rather than through it. The river sets the conditions. The tube accommodates them or reroutes. The river does not reroute. Water chemistry as operational parameter. The Yucatan's underground water is not chemically inert. It is calcium bicarbonate type water, mildly alkaline, carrying dissolved mineral load from its passage through the limestone, thermally stable at the cave's mean annual temperature of approximately 25 degrees Celsius in the freshwater zone and marginally cooler in the saltwater zone below the halocline. These properties are benign relative to the worst conditions any structural material in the installation faces. The anoxic zone's hydrogen sulfide chemistry is the installation's most demanding chemical environment, and the freshwater zone's calcium bicarbonate chemistry is mild by comparison. The calcium bicarbonate water has one property that accumulates into an engineering concern over the design life timescales Pipedream is committed to: mineral precipitation. Where flow velocity decreases, at passage constrictions, in the lee of structural elements, at surfaces that serve as nucleation sites for crystal growth, dissolved calcium carbonate can precipitate out of solution as calcite or aragonite crystals. The same process that formed the stalactites and stalagmites visible through the crystal tube walls is occurring on the tube walls themselves, on the anchor brackets, on the guide rail surfaces, on any surface in contact with the flowing water. The precipitation rate is slow. The formations visible through the tube walls took thousands of years to reach their current dimensions. But over the 1,000-year design life, unmanaged calcite precipitation on the crystal tube walls would accumulate to a thickness that measurably reduces optical transmission below the crystal specification. On the guide rail surfaces, calcite accumulation changes the rail geometry at the mechanical engagement points, affecting the cycle sub's emergency pedaling engagement and the maglev track's magnetic field geometry. The biological maintenance protocol addresses precipitation on the crystal tube walls. The Ancestris vitreous cleaning colony's enzymatic mucus is formulated to dissolve not just biofilm adhesive but mineral precipitation on the tube's optical surfaces. The enzyme package targets the carbonate crystal lattice, breaking the calcite deposit at the wall surface without attacking the wall material below it. The cleaning cycle that restores the wall to crystal specification for optical transmission simultaneously removes the weak's mineral precipitation accumulation. On surfaces the cleaning colonies cannot reach, the anchor brackets, the guide rail surfaces, the anchor pylon interfaces, a periodic chemical treatment protocol using citric acid solution is specified in the maintenance manual at a frequency calibrated to the mineral precipitation rate measured by the coordinating system's surface condition sensors. The citric acid chelates the calcium, converting the calcite deposits to soluble calcium citrate that washes away in the passage flow. The treatment is applied by maintenance drones during the low-traffic window in the early morning hours, timed to the minimum biological activity period the coordinating system's ecological census identifies for each passage zone. The mineral precipitation rate is also information. It tells the coordinating system where flow velocity has decreased relative to the baseline, because decreased flow velocity is the proximate cause of increased precipitation at a given location. A localized increase in mineral precipitation rate at a tube section that the coordinating system's flow model predicts should have maintained flow velocity indicates either a change in the upstream passage geometry, a new collapse reducing the passage cross-section, or a biological accumulation in the passage that is redirecting flow away from that section. Both conditions are worth investigating before they progress. The precipitation rate sensor network is simultaneously a flow regime monitoring system, and the flow regime monitoring system is simultaneously an early warning system for passage condition changes. The chemistry is continuous data. The data is continuously read. The streaming potential. Underground water flowing through narrow limestone passages generates electrical charge at the rock-water interface. The mechanism is electrokinetic. The limestone surface carries a fixed negative charge at the rock-water boundary, producing a diffuse layer of positive counterions in the water immediately adjacent to the surface. When flow moves this ion-enriched boundary layer downstream, it constitutes a convective current, charge moving in one direction, that produces a measurable electrical potential difference between the upstream and downstream ends of the passage section. This is the streaming potential. The physics has been known for over a century. The application to underground river systems as a practical energy source has not been pursued in the surface world because the surface world has no reason to be inside an underground river system at the scale that would make the harvest significant. Pipe dream is inside the system at the scale that makes it significant. The crystal tube network, running through passages where underground rivers flow, is already in contact with the rock-water interface that generates the streaming potential. The tube's anchor brackets, connecting the tube to the passage wall, are at the potential generating boundary. The guide rail, running along the passage floor through the flow, is in the ion-enriched boundary layer. The installation is geometrically positioned at the energy source without any additional infrastructure required to place collection electrodes at the generating surface. The streaming potential harvest system adds two elements to the existing crystal tube infrastructure: a conductive coating on the anchor bracket faces that contact the passage wall, a thin layer of corrosion-resistant conductor that captures the charge at the rock-water interface and transfers it to the collection circuit, and a collection bus running in the utility zone's data and power conduit alongside the data cables. The collection bus aggregates the streaming potential from all anchor brackets along a tube section and routes it to the power conditioning unit at the nearest cenote hub. The power output per tube section is small. The streaming potential's energy density is low relative to the surface world energy source's pipe dream's primary power infrastructure uses. The passage network is long. The underground river flows continuously, day and night, wet season and dry season, whether the civilization is demanding power or not. The aggregate streaming potential harvest from hundreds of kilometers of crystal tube anchor points in active flow passages is not the civilization's primary power source. It is the civilization's most distributed, most reliable, and most geologically durable supplementary source, the power that runs the sensor networks, the acoustic transceiver chains, the emergency lighting, the biological monitoring systems, and the breadcrumb navigation beacons in the deep passage zones where no other power source is available and where running a power cable from the main grid would require tube infrastructure that does not yet exist. The streaming potential is the formation's gift to the civilization's peripheral infrastructure. The formation is always flowing. The peripheral infrastructure is always powered. Biological corridor management. The underground river network is not an abiotic plumbing system. It is an ecosystem, a biological community that has operated in complete darkness, under stable temperature and pressure conditions, for periods longer than any surface ecosystem has been continuously inhabited by any continuous lineage of organisms. The cave fauna of the Yucatan's Anchialan systems represents millions of years of evolutionary divergence from surface relatives, blind, depigmented, metabolically adapted to low-nutrient conditions, distributed through the passage network in assemblages that reflect the passage history, which passages connected, when they connected, which populations were isolated by geological events that shifted the drainage network. The crystal-clear water of the Yucatan's cave systems, which the tourism industry presents as an aesthetic feature, is clear because it contains almost nothing. Low dissolved organic matter. Low suspended particulates. Low biological productivity in the pelagic zone, the open water column of the passage, away from the walls and floor. The biological community is concentrated at surfaces, the cave walls where microbial biofilms colonize every available substrate, the sediment interface where organic matter accumulates and detritivore communities process it, the halocline boundary where the chemocline creates a productivity gradient that supports elevated biological activity relative to either zone alone. Pipe Dream's biological management challenge in the passage network is two-directional. The installation introduces load to the passage ecosystem. The crystal tube's light relay system introduces photons to passages that have been dark since their formation, and photons drive primary productivity by any photosynthetic organism present, changing the community structure in ways that the digital twin's ecological succession model must predict and manage. The ancistrous vitreous cleaning colonies, operating in the freshwater passages, are a biological introduction into a passage ecosystem that evolved without any organism performing their enzymatic cleaning function. The community must accommodate them, and the coordinating system's biological census tracks the community's response. The installation also depends on passage ecosystem function. The biological community that has been processing organic matter in the passage sediments for millions of years is the reason the passage water maintains its chemical quality. Disrupt the community and the chemical quality deteriorates. The coordinating system's water chemistry monitoring includes biological community indicators, proxy measurements that reveal community health from water chemistry signatures without requiring physical disturbance of the sediment communities that the monitoring is designed to protect. The pink dolphin population, Aenia geofrensis, the bioengineered variant adapted for the freshwater passage network, are the most visible biological managers in the passage system. They are also the most active biological explorers. Their unfused cervical vertebrae allow passage through geometries that constrain other large body fauna, and their echolocation maps passage dimensions and obstacles in real time with a resolution no acoustic sensor array Pipe Dream has installed approaches. The coordinating system's passage network map, the digital twin's underground geography layer, incorporates dolphin echolocation returns, extracted from the acoustic data the biological monitoring network records from the dolphin population's movements through unmapped passages, as a continuous source of new passage geometry data. The dolphin population is, simultaneously, tourist attraction, biological management resource, and geological survey instrument. Their echolocation extends the known passage network faster than the lithocrustacean boring program can extend the occupied passage network. They go where the bores have not yet reached, and they return carrying acoustic data about what the bores will find when they arrive. The coordinating system processes the echolocation returns. The terraform operators interpret the processed data against the geological model. The boring program is allocated toward passages the dolphin data indicates will support crystal tube installation under the crystal tube standard structural requirements. The flood risk and the formation's authority. The underground river system that makes pipe dream possible can destroy pipe dream. This is known. It was known before the founding module's hydroprint was commissioned. It is in the founding charter's risk section, which is also the founding charter's design specification section, because every risk the formation presents is simultaneously a specification for the system that must accommodate it. The flood risk arises from the passage network's response to extreme rainfall events. The Yucatan's climate history includes hurricane-scale precipitation events that deliver in hours what the normal wet season delivers across weeks. These events are not outside the geological records range. The cave system's speleothem formations carry annual growth records that document the hydrological extremes of the past 10,000 years. The coordinating system's digital twin incorporates the speleothem paleoclimate record as the formation's own documentation of its hydrological behavior at extremes. In an extreme rainfall event, the cave network's recharge rate exceeds its discharge capacity. The rate at which the passage network can convey water to the coast is lower than the rate at which the event is delivering water to the network. The water table rises. The freshwater zone deepens rapidly. If the rise rate exceeds the ballast system's ability to adjust module buoyancy, a module at a fixed depth will experience a change in its position relative to the water table, floating higher relative to the cave ceiling as the water table rises, or submerging below a previously air-filled zone if the flooding is severe enough to push the freshwater surface above the cenote rim. The design response is not flood prevention. The formation cannot be told not to flood during extreme events. The design response is flood accommodation, the ability of every module in the installation to respond to a rising water table without structural failure or atmospheric compromise. The ballast system's flood accommodation mode is triggered by the coordinating system's rainfall monitoring and passage flow velocity data when the combined signal indicates an extreme event is in progress. In flood accommodation mode, the ballast tanks draw down to maximum positive buoyancy, modules rise with the water table rather than resisting the rising table from a fixed depth. The crystal tube connections between modules are flexible at the compensation joints, bellow section elements specified in the crystal tube standard for depth change accommodation, that allow the tube to follow module position changes without transmitting structural stress to the tube joints. The passive hydraulic rotary gates, the Venturi-triggered bulkheads that close on pressure differential from a breach, also respond to flood mode pressure conditions. The coordinating system's flood accommodation protocol sequences the gate openings to maintain atmospheric integrity in all occupied modules throughout the water table rise, allowing the gate positions to accommodate the changed pressure relationships between modules at different depths as the water table rises differentially across the network's geographic extent. The strontium illuminate rail markers that provide emergency navigation in the blackout protocol are also the flood accommodation protocol's navigation aids. A rapidly rising water table may produce turbidity from sediment suspension in passages where normally clear water flows, reducing visibility to near zero for any navigation that depends on visual observation of the passage environment. The rail markers glow in turbid water as reliably as in clear water. They are passive. They require no power. They do not need visibility ranges beyond the rail itself. They are the navigation system that functions in the worst hydrological conditions the formation can produce. The flood accommodation protocol is tested twice annually, once at the onset of the wet season, when the coordinating system runs the full protocol in simulation mode against the digital twin's flood scenario model, and once during the driest period of the dry season, when the modules are at their lowest water table positions and the simulation tests the protocol's performance at the opposite extreme. The protocol is not tested in a real extreme event for the first time when a real extreme event occurs. It has been tested against every scenario the formation's geological record indicates is within the range of actual occurrence. The flood risk is not managed. It is accommodated. The distinction is the founding charter's explicit position. The formation's authority over its own hydrological behavior is not negotiable, and any design that claims to manage, to constrain or control, the formation's response to extreme events is a design that has misunderstood the relationship between the civilization and the formation. The civilization lives in the river. The river will do what the river will do. The civilization's obligation is to be designed for it. The unmapped extent. The passages the coordinating system's digital twin documents are the passages the installation currently knows. They are not the passages that exist. The lithocrustacean boring program's acoustic transceiver chains, dropped at 50-meter intervals as the boring swarm advances through new tunnels, detect void signatures ahead of the advancing bore using acoustic reflection, The difference in acoustic impedance between solid limestone and air or water-filled voids is large enough that the transceiver chain's signal analysis identifies passage geometry at range, before the bore reaches the passage. The coordinating system maintains a forward extension of the digital twin, a projection layer derived from acoustic detections rather than direct observation, that maps the likely passage geometry ahead of the current bore fronts across all active boring operations. The forward projection layer consistently returns more passage volume than the boring program's expansion plan requires. The cave network ahead of the current installation extent is not a sequence of isolated chambers requiring connection by new bores. It is an existing connected network into which the boring program is advancing, finding passages that were already connected to each other, already carrying flow, already inhabited by the cave fauna that has occupied the network for millions of years. The boring program is not building connections. It is discovering existing connections and installing crystal tube infrastructure in them. This distinction has an implication the founding charter notes without further elaboration. The civilization's expansion is bounded not by what the boring program can build but by what the formation already contains. Pipedream cannot expand into a passage that does not exist. It can only expand into passages that do exist, are accessible to boring from the current network extent, and whose geological conditions meet the crystal tube standard's installation requirements. The formation has already determined the maximum extent of the civilization's possible expansion, before any expansion decision is made, by the geological history that produced the passage network. The maximum possible pipedream is the inhabited version of the passage network that already exists. Every expansion decision is a decision about which portion of that pre-existing network to inhabit next. The civilization does not grow into empty space. It grows into geological time. What exists beyond the current acoustic detection range of the transceiver chains is not known. The acoustic detection range is not the formation's extent. The formation's extent is whatever the dissolution process has produced in 66 million years of operation across the Chicxulub fracture network. The acoustic transceiver chains are detecting the nearest edges of this extent. What lies beyond the detection range is the question the boring program is advancing toward, one bore diameter at a time, at the acoustic cavitation rate the lithocrustacean colony sustains, in the direction the forward projection layer indicates is most likely to encounter major passage volume within the next boring session's advance. The founding charter does not claim to know the full extent of what the formation contains. It claims that Pipedream will learn it, that the boring program will advance, the transceiver chains will detect, the digital twin will record, and the forward projection layer will refine with every new bore, until the civilization's knowledge of the passage network beneath the Yucatan approaches the passage network's actual extent. How long this will take is not calculable. The formation has 66 million years of head start. The boring program is adding to the digital twin at the rate of 1 bore diameter per session. The asymmetry is acknowledged without embarrassment. A civilization that has committed to a 1,000-year design life has time to learn what it lives inside of. The rivers beneath the jungle have been running for 66 million years. They will be running when the boring program finds them. They will be running when the crystal tubes reach them. They will be running when the civilization that routes its crystal tubes through them has been operating for 500 years and knows the passage network well enough to stop being surprised by what the transceiver chains return from the dark ahead. The rivers are not waiting for Pipedream to discover them. They are doing what they have always done, flowing from the inland recharge zones to the Caribbean coast through the passages the limestone provided, and they will continue doing it whether Pipedream's boring program reaches them or not. Pipedream is the entity with something to gain from the encounter. The rivers are indifferent. The civilization that understands this is the civilization that approaches the unmapped extent with the same patience the trial window established at the founding, listening before entering, modeling before committing, asking what the formation will sustain before building anything inside it. The rivers have sustained themselves for 66 million years without being asked. They will sustain the crystal tubes for 1,000 more if the crystal tubes are installed in the passages the rivers have made rather than in passages the boring program wishes the rivers had made. Aquaforming, at the passage network scale, means following what the water has already carved. The civilization goes where the rivers went. The rivers went everywhere. Cross-references, Part 1, CH2, Y cenotes, Part 2, CH4, the Crystal Tube Standard, Part 3, CH2, Mapping the Great Aquifer, Part 3, CH3, Linking cenote to cenote, Part 4, CH5, The Living Tunnel Makers, Part 10, CH2, Electrochemical Harvest. For halocline depth monitoring protocol and flood accommodation mode activation parameters, see Appendix A, Formation Baseline Protocol. For streaming potential harvest system specification and collection bus integration with Crystal Tube Utility Zone, see Appendix B, Power Architecture and DC Bus. For lithocrustacean boring operations and acoustic transceiver chain deployment protocol, see Appendix D, Construction Operations Manual. For cave fauna community monitoring indicators and water chemistry proxy measurement protocol, see Appendix F, Biological Operations Manual. Pipedream. Part 3, The Living Underworld. Chapter 3, Linking cenote to cenote. Two cenotes are not a network. They are two experiments in the same geological substrate, operating on parallel timelines, accumulating separate formation models, generating separate habitation records, governed by separate Redeemer instance deployments that have not yet been asked to agree on anything. Two cenotes separated by 2 kilometers of unmapped passage are as isolated from each other, in every operational sense, as two surface world cities separated by a mountain range with no road between them. The mountain range of the cenote network is the limestone, the same limestone the lithocrustation boring program is advancing through, the same limestone the passive acoustic analysis is reading for passage signatures, the same limestone that has been dissolving for 66 million years and has produced, somewhere between any two cenotes in the Chicxulub-Arcs fracture zone, at least one connected passage path. Finding it is the first problem. Following it is the second. Installing the crystal tube connection through it is the third. Governing the moment when two separate installations become one network is the fourth. Each of these problems is distinct. Each has its own engineering and its own politics. None of them can be addressed in isolation because the solution to each constrains the solution space for the next. The connection between two cenotes is not an infrastructure project. It is a threshold event. Before the connection, two cenote installations. After the connection, one network node with two inhabited vertices. The threshold is the first occupied transit between them, the moment when the habitation record, which the principality's sovereignty claim rests on, extends continuously from one cenote's founding module through the crystal tube connection to the other cenote's founding module. Before that moment, two legal entities. After it, one inhabited territory. Every engineering decision in the linking sequence is also a political decision about when and how that threshold is crossed. The routing logic. The connection route between two cenotes is not drawn on a plan by an engineer with a straightedge. It is discovered by the acoustic mapping program and confirmed by the boring program's advance, following the formation's existing geometry rather than the straight line that Euclidean geometry would prefer. The straightest connection between two cenote installations would be a horizontal tunnel bored directly from one to the other at the most convenient depth, typically the freshwater zone, where the geology is most familiar and the biological management protocols are most mature. This tunnel, if the limestone between the two cenotes were uniform, competent, and free of major void intersections, could be bored by the lithocrustation program at a predictable advance rate, lined with crystal tube sections as the bore progressed, and completed in a timeline calculable from the bore diameter and colony output rate. The limestone between any two cenotes in the Chicxulub-Arcs fracture zone is not uniform, competent, and free of major void intersections. It is the same fractured, dissolved, differentially soluble karst that produced the cenotes at each end of the proposed connection, riddled with fractures running in the Chicxulub impact's preferred orientations, containing dissolution voids that range from hairline to room scale at unpredictable intervals along any proposed bore route, and honeycombed with passages carrying water at pressures and velocities the boring program cannot advance through without diverting the flow path first. The passive acoustic analysis of the intercenote zone, conducted from both cenote installations simultaneously, with the coordinating system cross-correlating the returns to triangulate passage locations between the two sensor arrays, typically identifies at least one major natural passage connecting the two cenotes before the boring program begins. In the Chicxulub-Arcs densest fracture zones, the analysis identifies multiple connected paths. The routing decision is not whether a natural path exists but which of the available natural paths the crystal tube connection should follow. The routing decision criteria, in the order of precedence the crystal tube standard specifies for intercenote connections. First, structural stability. The passage sections the route traverses must meet the geological stability rating threshold that the crystal tube standard's anchor specification requires. Passages in zones of active microseismic activity, passages with ceiling spans that the coordinating system's structural model identifies as at risk of collapse within the projection confidence interval's conservative bound, and passages crossing known dissolution active zones where the passage cross-section is measurably changing within the digital twin's historical comparison dataset. These are excluded from routing candidates regardless of how direct or convenient they are. A structurally marginal route that saves 2 kilometers of bore is not a shortcut. It is a site for the sacrificial collar to perform its function before the civilization is prepared for it to do so. Second, depth consistency. A connection route that maintains consistent depth within a single zone, preferably the freshwater zone for its superior biological management and less demanding structural specifications, or the halocline zone where the route's length makes surface-tier routing impractical, is preferable to a route that crosses zone boundaries multiple times. Each zone boundary crossing introduces the differential thermal expansion problem, the refractive index transition management problem, and the material specification transition problem documented in Chapter 3. Minimizing zone boundary crossings minimizes the number of these problems in a single tube installation. A route that crosses the halocline twice, descends into the saltwater zone, and reascends to the freshwater zone has 4 zone boundary transitions to manage. A route that maintains freshwater zone depth throughout has none. Third, passage accessibility. Natural passages that the lithocrustation boring program can enter with minimal enlargement work, where the existing passage dimensions are within the crystal tube standard's minimum annular clearance of the bore diameter, minimize the boring program's advance distance and therefore the connection timeline. A route through existing passages is faster than a route that requires new bores because each meter of new bore requires the lithocrustation colony to fracture, remove, and seal the limestone, a rate-limited process. Each meter of existing passage requires only the crystal tube installation sequence, cleaning, anchor placement, tube lowering, joint sealing, a significantly faster process. Fourth, flow regime compatibility. The connection route traverses passages that the underground river system uses as conduits. The flow velocity, direction, and variability at each passage section along the route determines the hydrodynamic loading on the crystal tube installation. A route through high-velocity passages during wet season peak flow requires more robust anchor specifications than a route through low-velocity lateral passages. Where routing choices exist, the coordinating system's hydrodynamic model selects the route whose worst-case hydrodynamic loading produces anchor requirements that the passage wall geology at that location can support. When these four criteria produce conflicting route rankings, when the structurally most stable route is the most depth inconsistent, or when the most depth-consistent route requires the longest new bore, the routing decision goes to the terraform operators of both cenote installations jointly, with the coordinating system's route analysis presented alongside the criteria rankings and the confidence intervals on each ranking parameter. The operators resolve the conflict with concurrent authorization, both operators' concurrence required before the routing decision is logged in the digital twin and the boring program begins. The joint terraform operator authorization for routing decisions reflects the connection's political character. The route choice commits both installations to a specific construction sequence, a specific timeline, and a specific set of geological risks. Neither installation's terraform operator can authorize the commitment unilaterally because the commitment is not unilateral. The connection belongs to both cenotes or it belongs to neither. The advance. The boring program's advance into the intersynody zone is operationally identical to its advance through any other new passage, the lithocrustation colony at the bore front, the acoustic transceiver chain dropped at 50-meter intervals to maintain data link, the swarm units behind the front seating crystal tube sections into freshly bored tunnel as the colony clears sufficient length for installation. The logistics differ from intersynody boring in one critical parameter, supply distance. In an intersynody bore, the boring front is within the cenote's internal passage network. Supply access, replacement calcium carbonate paste feedstock for the colony's tunnel sealing output, spare crystal tube sections for installation, swarm unit battery replenishment, terraform operator inspection access, is through the crystal tube network already installed in the cenote via maintenance sub. The maintenance sub navigates from the cenote hub to the boring front through installed infrastructure that connects the front to the hub. In an intersynody bore advancing into unmapped territory between two cenotes, the boring front is ahead of the installed crystal tube network. The front is accessible from the originating cenote through the installed network plus the uninstalled bore behind the front, an increasing length open bore through which the supply sub must navigate without the crystal tube's guide rail, without the maglev propulsion, without the safety systems that the installed crystal tube provides. As the advance progresses, the uninstalled bore segment grows. The supply sub's navigation in the uninstalled segment depends entirely on the acoustic transceiver chain for position reference and the strontium illuminate markers placed at intervals by the boring swarm for visual navigation. The advance rate is therefore constrained not by the boring colony's biological capacity alone but by the maximum uninstalled bore length at which the supply logistics remain safe for the maintenance crew. The crystal tube standard specifies this maximum for intersynody advance operations as the distance at which the supply sub's emergency air budget, the soda lime scrubbing capacity for the number of crew members in the sub, at the exertion rate emergency pedaling requires, without battery power, supports a return transit from the boring front to the nearest installed crystal tube section. When the uninstalled bore length reaches this maximum, the advance pauses. The swarm installs the next batch of crystal tube sections in the bored length immediately behind the boring front, extending the installed network toward the front. The supply sub's emergency return distance resets. The advance resumes. The installation program follows the boring program at the maximum safe separation distance the emergency air budget defines, the installed infrastructure advancing as fast as safety permits behind the advancing bore. This sequencing produces a specific relationship between boring rate and installation rate. The boring program is limited to advancing no faster than the installation program can follow at the maximum safe separation distance. A boring colony that can advance 3 meters per session but a crystal tube installation crew that can install only 2 meters of tube per session produces a net advance rate of 2 meters per session, the slower rate constraining the faster. The supply logistics optimization that matters for the connection timeline is not maximizing the boring colony's biological advance rate. It is balancing the boring rate and the installation rate to maximize the net advance rate at the separation distance constraint. The coordinating system's boring operations scheduler performs this balance continuously, allocating boring sessions and installation sessions across all active bore fronts in the network, not just the inter-synode connection bores but all concurrent boring operations, to maximize aggregate network expansion rate within the safety constraints at each bore front. The scheduler does not optimize any individual bore. It optimizes the total network. What happens when the bore meets a natural passage? The boring program's acoustic ahead sensing, the transceiver chain's forward-looking detection of void signatures ahead of the boring front, produces its most consequential data not in the steady advance through competent limestone but at the moment when the detection signature transitions from solid limestone to void. The void ahead of the boring front is either what the passive acoustic analysis predicted it would be, a natural passage of the dimensions and orientation the coordinating system's geological model assigned it, or it is different from the prediction in ways that the model did not anticipate. Both cases require the boring program to stop. The stop-on-void detection protocol is unconditional. The boring colony does not advance into a detected void until the terraform operator at the originating cenote has reviewed the void signature's acoustic characterization, compared it to the digital twin's geological model prediction, and issued a resume authorization that includes the specific safety conditions the advance into the void must satisfy. This protocol exists because the consequences of advancing a boring colony into an unexpected void are non-trivial. A large void with unexpected flow conditions can flood the boring tunnel in the time it takes the acoustic transceiver chain to relay the alert to the coordinating system. A void with unexpected H2S chemistry will kill the boring colony, which does not have the chemical resistance the anoxic zone's alone structural material provides. A void with a ceiling span beyond the geological stability model's prediction may be a pre-collapse chamber that the advance's acoustic disturbance contributes to destabilizing. The stop gives the coordinating system time to analyze the void signature at the detection range, before the bore enters the void, and update the digital twin's geological model with the new data. If the void matches the prediction, the resume authorization confirms this and specifies the advanced geometry the bore should adopt when entering the void, the compass heading that the connection route's routing decision specifies, confirmed against the void's actual orientation as the acoustic signature reveals it. If the void differs from the prediction, the terraform operator's review includes the divergence analysis and may require additional acoustic characterization from the transceiver chain's forward sensors before resume authorization is granted. When the bore enters a natural passage that is large enough for the crystal tube installation without further enlargement, the boring colony's role changes, from boring to sealing. The boring colony's calcium carbonate paste output, which in a new tunnel lines the fresh limestone fractures the acoustic cavitation opens, now lines the natural passage walls in the section the crystal tube will traverse, cleaning and smoothing the natural wall surface, filling hairline fractures that could propagate under the crystal tube installation's anchor loads, preparing the wall for the anchor bracket placement that the swarm units will perform once the paste has cured to the specified strength. The natural passage section that the bore has entered is now inside the installation, acoustically mapped by the transceiver chain, biologically assessed by the first water chemistry sample the chain's sensors take in the new void, geometrically characterized by the active ranging pulses from the chain's transceivers reflecting off the natural passage walls. The digital twin's aquifer layer updates in real time as the characterization data arrives. The forward projection layer, the hypothesis-level model the coordinating system had maintained for this zone based on passive acoustic analysis, is replaced by the confirmed observation layer derived from direct measurement. The confidence interval narrows from the wide passive analysis range to the tight active ranging range in the time it takes the transceiver chain to complete its first full characterization sweep. The natural passage is now known. It has been added to the knowledge the civilization carries about the formation it occupies. The boring program has not created the passage. The 66 million years of dissolution created it. The boring program discovered it and introduced it to the coordinating system's attention. The cave was here before the civilization. The civilization, by advancing into it, becomes responsible for it. The junction node. When the inter-synode bore advances close enough to the destination cenote that the destination's active acoustic ranging can detect the approaching transceiver chain directly, when the two acoustic sensor arrays can communicate with each other through the bore rather than through separate detection signatures, the bore has reached the junction zone. The boring program's advance rate drops to its minimum, single sessions of minimal advance, with full acoustic characterization after each session, and the terraform operators of both cenote installations assume joint operational authority over the final advance. The junction zone is where two crystal tube networks meet. The engineering requirement is straightforward: the last section of the originating cenote's crystal tube installation and the first section of the destination cenote's crystal tube installation must connect at a joint that meets the crystal tube standard specification in every dimension: optical, structural, acoustic, hydrodynamic, thermal. The same joint that connects any two crystal tube sections within a single cenote installation connects the two inter-synode networks at the junction. The junction node is the physical implementation of this connection, a structure designed to accommodate the geometry mismatch between the two crystal tube sections arriving from different directions, at potentially different depths, at potentially different rotational orientations, and to produce a connection that is geometrically continuous with both sections and structurally and optically indistinguishable from any other section of either network. The geometry mismatch is the junction node's primary engineering challenge. Intersynoody routing decisions specify compass headings and depths for the connection route, but the natural passage network the route follows is not a precision-machined corridor. By the time the bore from the originating cenote has navigated through the natural passage network for several kilometers and arrived at the junction zone, its actual depth and compass bearing may differ from the routing decision's specified values by accumulated navigation error, small angular deviations in the lithocrustacean colony's compass tracking that compound over the bore's length into lateral displacement at the destination. Simultaneously, the destination cenote's crystal tube network, if it has been extended toward the junction zone by boring from the destination cenote's side, carries its own accumulated navigation error in the opposite direction. The two bores' errors may cancel partially or may compound, depending on their specific error vectors. The junction node accommodates this by providing a geometrically flexible connection space, a chamber of sufficient volume that two crystal tube sections arriving from different directions can be aligned within it and connected through a junction collar that the junction chamber's geometry allows to flex across the angular and lateral displacement range the navigation errors produce. The junction collar is not a rigid tube section. It is a bellow section element, the same compensating joint the crystal tube standard specifies for depth change accommodation in vertically tiered connections, extended to a length that accommodates the three-dimensional displacement range the navigation error statistics, derived from the boring program's accumulated advance records across the full network, predict at 95% confidence. The junction chamber is the most complex single structure in the crystal tube network. It is also, once installed, one of the least visible, a node in the intersynody passage network through which maintenance subs transit without pause, in which guests in standard transit mode spend 30 seconds of their journey between cenotes without being aware they are in a junction rather than a standard tube section. The junction chamber's complexity exists in its geometry and its construction sequence. Once operating, it is a piece of crystal tube through which everything passes transparently. The governance threshold. The physical connection between two cenotes is a construction event. The governance threshold it creates is a constitutional event, managed under the Redeemer Framework's Inter-Instance Federation Protocol. Two separate cenote installations operating before connection each run their own Redeemer governance instance, their own conflict resolution platform deployment, their own Terraform operator concurrent authority structure, their own commons governance for the biological protocols and formation intelligence data each installation has generated. These instances are not isolated. The Redeemer platform's architecture allows inter-instance communication and data sharing under terms each instance's governance council establishes. The founding installations are designed to share formation data across the network from the beginning of the mapping program, because the digital twins aquifer layer requires observations from all installations to build its network-wide formation model. But data sharing between separate instances is not the same as governance integration. Two installations sharing formation data remain two separate principality territories until the habitation record connects them through the crystal tube junction. The moment of first occupied transit between them is the moment when Redeemer's inter-instance federation protocol activates, when the two instances, which have been communicating at the data sharing level, are asked to establish the governance integration that a single connected habitation territory requires. The federation protocol does not merge the two instances into one. Merger would require one instance to subordinate to the other or both to dissolve into a new combined instance, options that the Redeemer framework treats as the constitutionally significant choices they are, requiring referenda of both installations' citizenries rather than administrative decisions by governance councils. The Federation Protocol instead establishes a federated governance layer, a joint authority over the connected network's shared infrastructure, the crystal tube connection itself and its maintenance, the intersynody biological corridor management, and any commons assets that the connection makes jointly accessible, while leaving each installation's internal governance to its own instance. The federated layer is thin at first connection. The crystal tube connection between two cenotes creates shared infrastructure of limited scope, the junction node, the tube sections traversing the intersynody passage zone, and the biological corridor that the connection creates by linking two previously separate freshwater ecosystems. The federated governance authority covers these shared elements. Everything else remains within each installation's own instance jurisdiction. The federated layer thickens as the connected network grows. A three-synody network has three bilateral federation agreements, each covering the specific intersynody connection between the pair it governs. A 10-synody network has a federation architecture more complex than any bilateral protocol can manage. The Redeemer platform's multi-instance federation mode establishes a network governance council with delegated authority over the shared infrastructure across the full connected network, with each installation's instance retaining representation on the network council proportional to its habitation record's extent and duration. The Founding Charter's Sovereignty section describes the Network Governance Council as the principality's primary governing body at the stage of network maturity where intersynody connections have made the connected territory more coherent than the sum of its individual cenote installations. That stage is not reached at first connection. It is reached when the network's connections create more shared infrastructure than any individual installation's internal infrastructure, when the crystal tube network linking cenotes is more extensive than the crystal tube network within any single cenote. At that point, the Network Council's authority over the shared infrastructure is the Civilization Ally dominant governance function, and the individual installation instances are the Network Council's administrative subdivisions rather than the primary governance units. The founding charter anticipated this transition and structured Redeemers Federation Protocol to produce it organically, without a constitutional convention, without a ratification process, without any deliberate decision by any governance body. The transition happens when the facts of the network's physical extent make the Network Council the appropriate governance structure. Redeemer counts the shared infrastructure, compares it to the individual installation infrastructure, and flags the transition threshold when the ratio crosses the specified parameter. The Terraform operators of all connected installations are notified. The transition is confirmed by the network's governance councils in concurrent authorization, all installations concurrent, not majority, because a constitutional transition in a sovereign principality is not a decision that any subset of the principality's citizens can impose on any other subset. The threshold has not yet been crossed in Pipedream's current operational state. The network is still at the stage where individual cenote installations dominate their bilateral federation agreements. But the Digital Twins network expansion projection layer shows the threshold, and the forward projection shows the stage of network development at which the transition is anticipated, with the confidence interval that the projection's assumptions warrant. The Terraform operators know when the transition is expected. The governance councils know when the transition is expected. Redeemer's ready for it when it arrives. The biological corridor. Two cenotes connected by a crystal tube are two cenotes connected by an inhabited passage. The inhabited passage is inside an aquifer passage that was already occupied by the cave biological community before the crystal tube installation arrived. The crystal tube's installation in the passage does not remove the passage's biological community, it installs alongside it, in the annular clearance between the tube exterior and the passage wall, where the limestone surface's biological colonization continues regardless of the crystal tube's presence in the passage's center. The connection creates a biological corridor between two previously isolated freshwater ecosystems. Before the connection, the biological communities of the two cenotes were separated by however many kilometers of inter-cenote passage the connection route traverses. Gene flow between the communities depended on passive transport, organisms or propagules carried by the underground river's flow from one cenote's drainage basin toward the other. Gene flow by passive transport over kilometers of cave passage in a slow-flow regime is minimal. Most organisms that enter the inter-cenote passage from one cenote either settle in the passage itself or are consumed before reaching the other cenote. The result is population isolation, two communities of the same cave species accumulating genetic divergence through independent evolution at each cenote. The crystal tube connection changes this. The maintenance subs that transit the connection carry water from one cenote into the other, in the ballast systems, in the cleaning equipment, in the biological monitoring equipment, in the wetsuits of any scavenger-equipped personnel transiting the connection. This inadvertent transport is the minimum biological exchange the connection produces. The Ancestors vitreous cleaning colonies, which the coordinating system's biological management protocol now needs to manage across a connected freshwater corridor rather than within isolated cenote boundaries, are a more significant source of biological exchange. Cleaning colony individuals that enter the crystal tube in one cenote for maintenance operations may be transported to the other cenote in the maintenance sub's water systems before the coordinating system's location tracking identifies the individual as being in the wrong installation. The biological corridor's creation is an ecological event with implications the Digital Twins ecological succession model must incorporate before the first transit, not after. The pre-connection model assumes isolated populations at each cenote. The post-connection model must account for genetic mixing between previously isolated populations, for the potential introduction of one cenote's biological colonizers into the other cenote's maintenance-naive surfaces, and for the pink dolphin population's response to a freshwater corridor that, if it traverses the full depth range of the freshwater zone, allows dolphin individuals to transit between cenotes for the first time. The pink dolphin transit question is the most operationally significant biological corridor question. The freshwater zone's dolphins are managed populations, their home ranges are tracked by the biological monitoring network, their movements are influenced by the coordinating system's light array behavioral deterrence at the halocline boundary, their food supply is supplemented by the aquaculture gallery's spillage and by managed prey introduction. A managed population in a single cenote's freshwater zone is an ecologically bounded system. The dolphin's home range corresponds to the cenote's accessible freshwater volume, and the coordinating system's management interventions are designed for that bounded volume. A crystal tube connection that traverses the freshwater zone, that passes through passages at depths above the halocline throughout its length, creates a freshwater corridor that the dolphin's unfused cervical vertebrae and echolocation-based navigation are capable of using. A dolphin individual that enters the crystal tube connection corridor and navigates through it to the other cenote's freshwater zone has arrived in a space with a different managed population, a different aquaculture gallery layout, a different light field signature from the coordinating system's illumination arrays, and a terraform operator who was not expecting a visitor from the adjacent installation. The Biological Corridor Management Protocol specifies, for intercity connections at freshwater zone depth, the installation of behavioral deterrent arrays at the connection's entry points on both cenote sides, the same light array deterrent the coordinating system uses at halocline boundaries to prevent dolphin crossings, now used at the crystal tube junction's freshwater zone entry to manage intercity transit at the population management level rather than the individual level. Managed intercity dolphin transits, for genetic exchange, population balancing, or coordinated survey operations, are scheduled by the two installations' terraform operators jointly and are accompanied by temporary deactivation of the deterrent arrays at both junction entries for the duration of the scheduled transit. Unmanaged transits are deterred but not prevented. A dolphin that is sufficiently motivated to cross through a temporarily active deterrent field, which the light array does not guarantee will deter every individual under all behavioral states, is a dolphin the coordinating system's tracking network will identify as being in the wrong installation within minutes of crossing the deterrent threshold. The terraform operator notification is automatic. The recovery protocol, safely guiding the transited individual back through the connection, is in the Biological Operations Manual. The protocol's tone toward unauthorized dolphin transits is management, not punishment. The dolphin that crosses the deterrent is not malfunctioning. It is doing what dolphins do in a connected aquatic environment, exploring. The coordinating system and the terraform operators are the entities that need the populations to be managed. The dolphins have their own priorities, which the management system accommodates as far as possible while maintaining the population structure that the biological management protocol requires. The depth variable connection. A crystal tube connection that traverses only the freshwater zone, maintaining constant depth from junction to junction, is the engineering ideal. The routing decision criteria establish depth consistency as a priority precisely because depth variable connections introduce every complication the depth consistent connection avoids. The Yucatan's passage network does not consistently provide freshwater zone depth passages between cenotes. The karst's dissolution history followed fractures and bedding plains that dip and rise with the peninsula's subtle topography. Passages that enter the freshwater zone at one cenote may descend through the halocline and into the saltwater zone at intermediate depths before rising again to freshwater zone depth at the destination cenote. The passive acoustic analysis of the intercity zone typically reveals the depth profile of the available natural passages before the routing decision is made, allowing the routing decision to select a depth-consistent route if one exists. When no depth-consistent route exists, when the passage network between two cenotes requires a halocline crossing regardless of routing choice, the connection design must accommodate the depth variation while maintaining the crystal tube standard's performance across all zones the connection traverses. The depth variable connection's additional engineering complexity concentrates at the zone transitions. A crystal tube section that descends through the halocline carries the PMMA to polycarbonate material transition at the halocline's upper boundary and a second polycarbonate to aluminosilicate glass transition if the descent reaches the structural depth zone. Each transition requires the index matching adhesive management, the thermal accommodation polymer specification, and the visual transparency maintenance that Chapter 3 documents for intercity zone transitions, now applied in a tube section that the maintenance crew reaches after a multi-kilometer transit rather than after a short intercity navigate. The depth variable connection's maintenance accessibility is therefore the primary operational constraint that intercity depth changes impose. An intercity zone transition that requires a maintenance intervention is accessible from the cenote hub within the emergency air budget of a standard maintenance sub. An intercity zone transition kilometers from either cenote hub may be outside the emergency air budget's return distance range, making emergency maintenance intervention during a connection failure event a different planning problem than the intercity equivalent. The connection design response is intermediate hub deployment. At the deepest point of a depth variable connection, the point furthest from both cenote hubs in maintenance response time, a minimal hub structure is installed, not a full cenote installation, not a habitation module, but an emergency refuge station providing atmospheric air replenishment, battery charging, emergency equipment storage, and a communication node that connects to the coordinating system through the crystal tube's data conduit. The emergency refuge station converts the maintenance response problem from a single-leg emergency transit from the nearest cenote hub to a two-leg transit in which the refuge station is the intermediate supply point. The refuge station is also a passive monitoring node, carrying the sensor package that the crystal tube standard requires at every hub point in the network, providing the coordinating system with local formation data from the intercity passage zone that neither cenote hub sensor arrays reach at sufficient resolution. The emergency function and the monitoring function share the same installation, the same power supply from the streaming potential harvest network that the crystal tube's anchor brackets feed from the intercity passage flow, and the same crystal tube connection infrastructure they serve. A refuge station is not a founding module. It does not have a trial window. It does not generate a habitation record. It is not a cenote installation in any legal or political sense. It is a maintenance resource and a sensing node, the civilization's infrastructure serving the infrastructure. Its installation does not require terraform operator expansion authorization because it is not an expansion of the inhabited territory. It is support for the connection that the terraform operators authorized. The distinction between habitation and support infrastructure is constitutionally specified in the Redeemer framework and ecologically specified in the Hydroprint method. Habitation means continuous human occupation, generating a habitation record, creating the legal and ecological responsibility that accompanies the sovereignty claim. Support infrastructure that is not continuously occupied does not create a habitation record. The refuge station is visited by maintenance crews on the maintenance schedule the connection design specifies. Between visits it is empty. The cave biology colonizes its exterior surfaces on the same schedule that colonizes any other installed surface. The ancestors vitreous colonies included in the refuge station's biological management package clean those surfaces on the same schedule the coordinating system allocates against the same optical transmission monitoring it applies across the full crystal tube network. The formation does not distinguish between inhabited and uninhabited surfaces in its biological colonization behavior. The civilization distinguishes between them in its legal and governance architecture. The biological management protocol manages both because it manages surfaces, not legal categories. The first transit. The operational commissioning sequence for an intersynody connection concludes with the first occupied transit, the event that converts the connection from an installed infrastructure component into a principality territory boundary traversal. The event is not ceremonial. The Redeemer governance framework logs it as a legal record, the timestamp at which the habitation record extends through the connection, the identification of the occupied vehicle and its crew, the confirmation that all crystal tube standard performance parameters were met during the transit, and the Terraform operator's concurrent authorization that the transit constituted the first legally valid habitation record extension through the connection. The transit is also a biological event, the first movement of crew members, their water systems, their equipment, through the biological corridor the connection has created. The biological monitoring protocol logs the pre-transit biological census at both cenotes and schedules the first post-transit census for 30 days after the first transit. The 30-day interval is the minimum period in which introduced biological material, organisms, propagules, chemical signatures, would be expected to produce detectable changes in the receiving cenote's biological community if any were introduced during the transit. The transit is also a physical event with no precedent in the installation's history, the first time any water mass carried by a vehicle moves between two cenotes that were previously hydrologically isolated from each other at the accessible passage depths. The underground river system connects them hydrologically through the deep passage network, but the surface freshwater communities of both cenotes have evolved in isolation from each other because no accessible surface passage connected them before the crystal tube installation. The first transit breaches that isolation irreversibly. The coordinating system's biological model acknowledges this irreversibility explicitly. Preconnection isolation is a historical state that ends with the first transit. It cannot be restored by removing the crystal tube connection. The passage network exists, the organisms transported during the first transit exist in the receiving cenote's water column, the biological corridor is open. The preconnection model is archived as a historical reference. The post-connection model begins accumulating data from the first transit's biological census logs. This irreversibility is the reason the biological corridor management protocol's pre-transit requirements are more demanding than any other pre-operational check in the installation's commissioning sequence. The maintenance sub that makes the first occupied transit is inspected for biological contamination, any living material attached to its exterior surfaces, any water retained in its mechanical systems that could carry biological matter between cenotes, more thoroughly than any maintenance sub inspection in normal operations. The crew's equipment is inspected for the same. The transit represents the moment before which biological mitigation is possible and after which it is not. The Terraform operators of both cenote installations jointly authorize the first transit. Their concurrent authorization is the last checkpoint before irreversibility. The authorization confirms that the biological corridor management protocol's pre-transit requirements have been met, not as an administrative confirmation but as a personal professional judgment by two Terraform operators who have been trained in ecological succession, who understand what irreversible biological exchange means for two cenote communities that evolved in isolation, and who accept professional responsibility for the management of that exchange from the moment their authorization is logged. The first transit takes as long as the crystal tube connection's length and the maintenance sub standard transit speed require. It passes through the junction chamber, through the intersynody passage zone, through the biological corridor's natural passage sections and board sections, through the refuge station if the connection includes one, and arrives at the destination cenote's crystal tube entry with the crew who left the originating cenote still inside it. No ceremony marks the arrival. The coordinating system logs the timestamp. The Redeemer governance instance records the habitation extension. The biological monitoring network begins the 30-day post-transit census protocol. The Terraform operators at both cenotes receive the completion notification. Two cenotes are now one network. The civilization that was two experiments has become one body. The topology that emerges. No design document specifies the pipe dream network's connection topology. No founding engineer drew a map of which cenote would connect to which and in what sequence. The topology emerges from the formation's passage geometry, from what the passive acoustic analysis reveals about which cenotes have natural passage connections between them, from what the routing decision criteria determine about which available connections are viable, from what the hydroprint campaigns reveal about which proposed cenotes reach readiness in which sequence, and from what the boring program's advance history accumulates as the practical knowledge of which geological contexts support rapid advance and which require the minimum advance caution the void detection protocol mandates. The topology that emerges is not the topology that a surface world engineer would design for a network connecting the same cenote locations. A design topology would optimize for shortest total connection length, or for redundant connectivity ensuring no single connection failure isolates any installation, or for balanced load distribution across the network's transit capacity. All of these are valid engineering objectives for a designed network. The formation does not optimize for any of them. It offers what 66 million years of dissolution produced, a passage network whose topology is the geological record of which fractures dissolved fastest, which bedding planes were most soluble, which karst dissolution fronts propagated most actively toward each other. The civilization follows this topology because it is what the aquaforming doctrine requires, the infrastructure conforms to the formation, and because the topology the formation offers, while not optimized for any specific engineering objective, is available without boring, is structurally validated by its own geological survival history, and is known through the acoustic mapping program at a fidelity the boring program cannot match in the time available. The network that the formation's passage topology produces may have cenotes that are more densely connected to adjacent cenotes than any designed network would specify, clusters of closely spaced cenotes in the Chicxulub arc's densest fracture zones, where multiple natural passage connections exist between each pair and the connection topology is mesh-like rather than linear. It may have cenotes more isolated from their nearest neighbors than any designed network would tolerate, cenotes at the periphery of the fracture zone where the passage network is less dense and the nearest natural connection requires a longer bore than the dense central zone requires. These are the formation's topological decisions. The civilization's response is to manage the sparse connection cenotes differently from the dense connection cenotes, not as an admission that the network is suboptimal but as the operational recognition that different geological contexts produce different network roles. A centrally located, multiply-connected cenote hub carries intercenote transit traffic in addition to its own habitation and tourism operations. A peripherally located, singly connected cenote, a living pantry corridor installation at the end of a single crystal tube connection from the nearest hub, carries only its own traffic, which the single connection can serve. The peripheral cenote's geological isolation determines its operational role. The operational role is designed to fit the geological reality rather than being designed to override it. A network topology that emerges from geological reality is a network topology that does not require geological reality to be different from what it is. Every design topology that does not fit the geological reality requires that reality to be changed, by boring connections where no natural passage exists, by bridging geological stability zones that the routing decision criteria exclude, by forcing connections through depth profiles that produce zone boundary crossings the maintenance logistics do not support. These changes are expensive, slow, and geologically presumptuous. They impose the design's requirements on the formation rather than adapting the design to the formation's offer. Pipedream's network grows into the topology the formation offers. Some connections are fast because the natural passage network provides them easily. Some connections are slow because the passage network requires significant boring to achieve them. Some connections wait for formations whose hydroprint readiness signal has not yet arrived. The network's shape on the coordinating system's aquifer layer display is not the shape a network designer would have produced. It is the shape the limestone has made available across 66 million years of dissolution, occupied one connection at a time by a civilization that asked before it entered what the formation would allow. The formation's topology is the civilization's map. Not the map the civilization would have drawn if asked to design it. The map the formation drew, in the same process that drew the cenotes, the passages, and the rivers. The civilization followed it. Cross-references, Part 2, CH4, The Crystal Tube Standard, Part 3, CH1, Rivers Beneath the Jungle, Part 3, CH2, Mapping the Great Aquifer, Part 3, CH4, Underground Boulevards, Part 4, CH5, The Living Tunnel Makers, Part 9, CH2, Floating Title and the Habitation Record, Part 9, CH6, Distributed Sanctuary and the Physics of Privacy. For intercenote boring operations advance rate protocol and supply logistics safety constraints, see Appendix D, Construction Operations Manual. For redeem inter-instance federation protocol and network governance council transition threshold parameters, see Appendix H, Governance Operations Manual. For biological corridor pre-transit inspection protocol and 30-day post-transit census methodology, see Appendix F, Biological Operations Manual. For depth variable connection refuge station specification and intermediate hub installation protocol, see Appendix D, Construction Operations Manual. Chapter 4, Underground Boulevards. A boulevard is not a road. The distinction matters because the surface world has spent 3 centuries conflating them, designing roads for vehicles and calling the result a public space, then wondering why the public space produces no public life. A road moves traffic between points. A boulevard moves people through space. The difference is not speed or volume or lane configuration. It is whether the infrastructure acknowledges that the people inside it are experiencing something, and designs the experience rather than merely the throughput. The Crystal Tube Network's transit function was specified before the network existed. The Crystal Tube Standard defines the transit zone's dimensions, the guide rail's geometry, the maglev propulsion's performance parameters, the bypass vent's acoustic management. These specifications produce a functional transit system. They do not produce a boulevard. The boulevard emerges from what the Crystal Tube Standard specifications happen to produce when combined with the cenote environment's visual and biological conditions and the civilization's stratified social topology, not from any explicit design intention to create public space, but from the accumulation of correct engineering decisions each made for independent reasons. This is what aquaforming produces when it is applied consistently enough. Design intentions that were never stated become properties of the system that the system's users experience as facts of the environment. The formation's visual continuity through transparent tube walls was preserved because opacity would have interrupted the civilization's ability to see when the formation required attention. The biological corridor's management produces a living display alongside the transit route because the biological systems require the same water chemistry and light conditions that the transit zone's inhabitants experience. The light cannon relay makes the transit luminous because the formation requires illumination for the coordinating system's biological census operations, and the relay infrastructure serves both functions from the same installation. The boulevard that results from these decisions is not designed. It is inevitable. The engineering that produced it was solving other problems. The public space it creates is what those solutions look like from inside a pod in transit. What transit is in a cenote network. Surface world transit systems connect points of concentration, neighborhoods, employment centers, civic facilities, across distances that make walking impractical and private vehicle use collectively unsustainable. The transit system's social function is to permit the city to be larger than walking distance while remaining functionally connected. The experience of transit is incidental to this function. The urban rail passenger is not on the train to experience the train. The train is the cost of getting from one place to another in a city too large to walk. Pipe Dream's transit function is different in a specific way that changes the experience's character entirely. The intercity connections are not traversed because walking through them is impractical. Walking through them is impossible. The intercity passage is flooded, kilometers long, navigable only by sub. The Crystal Tube connection is not an alternative to walking. It is the only means of transit between cenotes. There is no parallel path. There is no surface road above the passage network connecting the cenote installations. The jungle's surface is interrupted by cenote openings but not by roads between them. The transit system is not a convenience. It is the civilization's sole medium of intercity movement. This exclusivity produces a transit culture that has no surface world equivalent. Every person who moves between cenotes in the Pipe Dream network moves through the Crystal Tube. The terraform operators making their rounds between installations. The longevity program guests being transferred from a formation cenote's halocline gallery to a corridor cenote's living pantry for a supervised observation session. The aquaculture harvest crews moving between production nodes. The governance council members transiting for the joint terraform operator authorization that the network's expansion decisions require. The maintenance technicians carrying cartridge replacement loads to deep gallery installations in one cenote from the fabrication hub in another. The adventure guests on multi-cenote itineraries designed specifically to use the transit system as the primary experience rather than as the means to reach an experience. The transit system is not incidental to the civilization's life. It is the civilization's connective tissue, the medium through which the network functions as a single body rather than as a collection of separate experiments. What happens inside the Crystal Tube during transit is not the background to more important activities occurring at destinations. For the time the transit takes, the tube is where the civilization's life is happening. A civilization whose life happens in its transit system needs its transit system to be a boulevard. The speed question. The maglev propulsion system's performance parameters were specified for functional transit: the electromagnetic field's repulsion force, the guide rail's indic-track geometry, the pod undercarriage's Halbach array configuration, together establishing a maximum transit speed that the Crystal Tube Standard ratifies as the ceiling for normal operations. The ceiling is not high by surface world transit standards. The cenote network's geometry, the curves that passage routing imposes on tube alignment, the depth changes at zone transitions, the junction node's reduced speed requirement, constrains the average transit speed regardless of the maximum the propulsion system can achieve in a straight horizontal section. The speed question in the boulevard context is not whether the system can go faster. It is whether faster is the right parameter to optimize. A transit system that moves people through a geological formation of extraordinary visual and biological complexity at the maximum speed the propulsion physics allows is a transit system that treats the formation as a medium to be traversed rather than a space to be inhabited. The passenger who crosses 2 kilometers of aquifer at 40 kilometers per hour sees the formation at 40 kilometers per hour, a blur of limestone and bioluminescence and schooling fish that registers as spectacle without resolution. The crystal tube standard specified normal operating speed for occupied transit is not the maximum the propulsion system produces. It is the speed at which the visual experience through the tube walls achieves a quality the coordinating system's passenger experience monitoring identifies as legible, the speed at which a passenger looking through the tube wall can identify the biological community type in the passage beyond the wall, can track an individual Ancistrus vitreous colony member's movement along the wall surface, can watch the halocline's optical dissolution effect develop over the seconds of transit through the halocline zone rather than perceiving it as a momentary blur. The speed is designed for the experience, not for the throughput. Throughput in the pipe dream network is not the binding constraint. The network's population density and intercity transit demand do not approach the crystal tube's passenger capacity at any projected expansion stage within the 1,000-year design life's first century. The system is not crowded. The speed does not need to be maximized to serve the demand. The speed can be, and is, chosen on the basis of the experience it produces. The exception is the maintenance sub and scheduled maintenance transit, the same guide rail at the same tube, carrying a maintenance crew and a cartridge load on a time-constrained maintenance window, moves at the maximum speed the geometry allows. The maintenance sub does not take the boulevard speed. It takes the functional transit speed. The coordinating system's traffic management protocol distinguishes between boulevard transit, occupied by guests, longevity program participants, governance personnel, any transit that is itself a principality experience, and functional transit, managed at functional speed. The two modes share the same infrastructure and the same guide rail. They do not share the same speed. The boulevard is what the crystal tube becomes when the speed is correct for experience rather than throughput. The visual sequence. A transit between two formation cenotes 3 kilometers apart, at the boulevard's normal operating speed, takes approximately 14 minutes. The visual sequence those 14 minutes contain is not uniform, it changes with the passage geometry, the depth, the biological community, the lighting conditions, and the junction and refuge station nodes the route traverses. The sequence is predictable because the digital twin's aquifer layer knows the route's full geometry and the coordinating system's biological census knows the passage's current biological community at each section. But it is not identical on any two transits. The biological communities shift with the seasonal cycle, the halocline's depth changes with the hydrological regime, the light cannon relay's intensity varies with the surface lighting conditions that determine how much energy the relay has to propagate. The first section of the transit emerges from the originating cenote's hub into the crystal tube corridor that extends horizontally through the freshwater zone. The transition from the cenote's open water volume, where the guest has arrived by cycle sub from the founding module's surface tier or descended through the hyperized transit gallery, to the intercenote crystal tube is a geometric transition from open space to enclosed corridor. The cenote volume is large, ceiling formations, cave walls at varied distances, the full three-dimensional visual field that the translucent hyperized outer galleries provide. The intercenote corridor is a cylinder 2 to 3 meters in interior diameter. The visual field contracts from the three-dimensional to the cylindrical. The psychological effect of this contraction is not claustrophobia for most passengers. The Terraform operator's pre-transit briefing and the pod's transparent hull address this, but it is a perceptual shift that the coordinating system's passenger experience monitoring tracks through biosensor data from the pod's interior sensors, heart rate, galvanic skin response, respiratory rate, all sampled throughout the transit. The monitoring produces a longitudinal dataset of passenger physiological response to each section of each route, updated after every transit, that the coordinating system uses to refine the light cannon relay's intensity schedule, the pod's interior lighting, and the audio environment the pod provides. The audio environment is not silence. The bypass vent tone, the acoustic signature of air moving through the pressure relief vents as the pod advances, is the transit's constant acoustic background, a broadband white noise adjacent sound whose frequency is in the band the acoustic zoning protocol placed above the structural health monitoring range. Over it, at low volume, the coordinating system feeds the pod's interior speaker array with the formation's own acoustic signature, the passive acoustic monitoring network's current recording of the intercenote passage zone's ambient sound, the low-frequency resonance of the cave chambers the route passes adjacent to, the occasional biological acoustic event from the cave fauna community in the passage walls beyond the tube. The passenger is not in acoustic isolation. They are inside the formation's sound, filtered to remove the maintenance and operational frequencies and presented at the volume the coordinating system's passenger experience monitoring identifies as enhancing rather than overriding the visual experience. The freshwater zone section's visual character is determined primarily by the biological community in the passage walls beyond the tube's transparent surface. If the route's freshwater section traverses a high-flow passage where the underground river runs at velocity sufficient to suppress heavy biological colonization of the walls, smooth limestone, sparse biofilm, the occasional invertebrate community in sheltered microniches, the visual field is largely geological, the passage wall's limestone texture at close range, the void of the passage cross-section beyond the tube and the illuminated cone of the light relay's projection ahead of the pod. If the route traverses a low-flow lateral passage where the biological community has had decades to establish undisturbed, the passage walls are biological architecture, layered microbial mats, stalactite formations colonized by sessile invertebrates, small fish species native to the cave hovering in the eddy zones behind the tube's anchor brackets, the ancestral vitreous cleaning colonies moving along the tube wall immediately outside the passenger's window. The pod is not hermetically sealed from the passenger's biological perspective. The tube wall is transparent. The biological community outside the tube wall is at the distance of the tube wall's thickness. The guest who presses their face to the tube wall to observe the ancestral vitreous colony working the surface is separated from the organism by the 12-inch effective equivalent of chemically strengthened aluminosilicate glass, a distance at which the colony members' chromatophore-shifted semi-translucency, the enzymatic mucus pattern on the tube surface, the individual's oral disc geometry are fully visible to the unaided eye. The biological spectacle at the tube wall is not behind glass in the sense of removed from the observer's sensory field. It is at glass, close enough that the glass is not a separation but a medium. The halocline transit. A depth-variable route that crosses the halocline is a transit through two visually distinct geological environments separated by the most optically anomalous natural boundary in the accessible cave system. The preparation for the halocline crossing happens in the final 100 meters of freshwater zone transit. The temperature at the tube wall, which the pod's interior thermal management system maintains independently of the outside water temperature, is stable. But the temperature differential between the pod's interior and the outside water is increasing as the freshwater zone's 25 degrees Celsius water approaches the halocline's temperature gradient. The passenger's awareness of this change is primarily visual. The light cannon relay's color temperature shifts subtly as the freshwater zone's optical properties change with depth, a shift the coordinating system programs into the relay as a transit orientation cue rather than an incidental property. The halocline's optical dissolution effect arrives through the tube wall before the pod enters the halocline zone. The dissolution effect is a property of the water outside the tube, the visual blurring where fresh water and salt water coexist in contact at the halocline boundary, and the tube wall transmits it as faithfully as any other property of the optical environment beyond the wall. The passenger looking through the tube wall into the passage water sees, first, a zone where the normally clear freshwater column acquires a shimmering indistinctness, edges losing their resolution, surfaces behind the near water acquiring the slight double image that different density media produce when light traverses them. Then, as the pod descends through the halocline zone, the effect intensifies to the full dissolution signature. The passage walls beyond the halocline's thickest stratum appear simultaneously present and absent, geometrically real but optically indeterminate. Limestone that the brain identifies as solid but cannot fix in space because the light that shows it has passed through two refractive index regimes and arrived carrying information from both simultaneously. This is the cenote network's most distinctive visual experience. It has no surface world equivalent because it requires a specific combination of conditions: fresh water above, salt water below, a stable boundary between them, an observer in a transparent enclosure at the boundary, that occurs naturally in only a few geographic contexts on the planet and is accessible by transparent enclosure only in the pipe dream installation. The halocline transit is not a byproduct of the depth variable connection. For routes that cross it, it is the route's signature experience, the moment the geology asserts its strangeness most fully and the transparent infrastructure's purpose is most completely demonstrated. The pod does not pause at the halocline. The coordinating system's transit schedule does not allocate dwelling time at the halocline zone for the standard transit mode. The halocline's location varies with the hydrological regime, and a scheduled pause at a fixed depth for a halocline observation would sometimes be in the halocline and sometimes not. The transit continues at boulevard speed through the halocline zone, and the dissolution effect develops and resolves in the time the depth variable descent takes to traverse it. For routes where the halocline transit is the destination experience rather than an incidental crossing, the coordinating system offers a halocline dwelling mode. The pod's ballast management, integrated with the crystal tube's depth positioning system, holds the pod at the halocline depth for a defined period while the exterior water provides the full dissolution effect through the tube wall. The dwelling mode is not standard. It is a scheduled experience, booked in advance, available at the Cenote Hub's Adventure Program desk, and subject to the coordinating system's halocline depth monitoring confirming that the current halocline is at the depth range within which the chosen tube section's dwelling mode can position the pod. If the halocline has migrated out of range, dry season shallow, wet season deep, the dwelling mode is rescheduled rather than performed at the wrong depth. The experience is specific. The formation sets the schedule. Junction nodes as civic space. The junction node, the chamber structure at the connection point between two inter-cenote crystal tube sections, is an engineering requirement. Its volume accommodates the geometry mismatch between arriving tube sections and provides the structural connection space the bellows section junction collar requires. It is sized to engineering requirements, not to social ones. It is also, once the network is operating, the only point in the intercity transit system where passengers from different origin cenotes encounter each other in the same physical space, where the transit system produces a meeting point. The surface world's transit system produces meeting points at stations, which are designed for the purpose: circulation space, waiting areas, retail, wayfinding infrastructure. The junction node is not designed for any of these functions. It is designed for crystal tube geometry accommodation. But a node where passengers from two or more cenotes can simultaneously be present, in a space of sufficient volume for interpersonal awareness, in the only inhabited space in several kilometers of underground passage, this is a social event regardless of whether it was designed as one. The junction node is where two passengers who departed different cenotes at slightly different times arrive at slightly different moments and share a space for the duration of the junction transit protocol, the speed reduction approaching the junction chamber passage at reduced speed, and the re-acceleration into the departing tube section. This is brief. The standard junction transit takes under 2 minutes from deceleration onset to full re-acceleration. The pods do not stop. The passengers do not interact. The shared space is traversed in sequence rather than simultaneously in most transit scenarios. The social event the junction node produces is not a sustained encounter. It is a glimpse, another pod visible through the junction chamber's transparent walls as one's own pod enters or exits, the awareness of other travelers in the same underground space, the civilization's connectivity made briefly visible as a visual fact rather than an abstract claim. The Terraform Operator's Network Expansion Planning Log contains no record of any discussion of the junction node's social function during the connection design phase. The junction node was designed for its engineering function. The social function emerged from the transit behavior of the civilization that uses it. The coordinating system's passenger experience monitoring noticed the effect, a measurable change in passenger biosensor data at junction node passages consistent with heightened alertness, social recognition, and in some cases the physiological signature of surprise, before any Terraform operator had articulated it as a design observation. The monitoring data produced a design response. The junction chamber's light cannon relay configuration was modified from the standard intercenote tube illumination pattern to a wider cone, higher diffusion illumination that made the chamber's full interior visible to occupants of all pods in the chamber simultaneously, rather than the directional forward illumination pattern appropriate for linear transit. The modification increased junction chamber ambient light by the factor the coordinating system's monitoring indicated maximized the social awareness response without producing the glare that made sustained viewing of other pods' occupants uncomfortable. No design document specifies this modification as a social design intervention. The coordinating system's maintenance parameter update that implemented it describes it as an optical transmission optimization. The optical transmission optimization was a design decision about public space made in the language of engineering requirements. This is how the civilization designs its public realm without designing its public realm. The coordinating system notices what the formation and the occupants together produce, and adjusts the parameters to improve the outcome, in the language of the parameters it controls. The boulevard is designed in real time, continuously, by the system that manages it, from the data the occupants produce by using it. No architect's vision is consulted. The formation's conditions and the occupants' biological responses are the design brief. The living pantry as boulevard destination. The corridor cenote connection routes that traverse living pantry installations are the network's most visually programmed boulevard sections. The living pantry's aquaculture galleries, the suspended mesh cylinders, the spirulina bioreactor columns, the freshwater lobster pens, the autonomous harvest drone lanes, are not installed in the transit tube itself. They occupy the passage volume surrounding the crystal tube, in the annular space between the tube exterior and the passage walls, viewable through the tube walls in the same way the biological community of any passage section is viewable. The transit route through a living pantry section passes through the center of the food production infrastructure. The production infrastructure is the visual environment. The visual programming of this section is determined by the aquaculture management protocol's production requirements, which species are in which gallery at which growth stage, what the current harvest cycle's timing is, how the drone lanes are loaded, rather than by any transit experience design intent. The production requirements that produce the visual sequence are optimized for food production efficiency. The visual sequence they generate as a byproduct is what the coordinating system's passenger experience monitoring identifies as producing the highest sustained passenger engagement of any section in the network, longer average gaze duration at specific visual elements, lower physiological stress indicators, higher self-reported satisfaction scores in the post-transit questionnaire that the longevity program's research protocol collects from enrolled guests. The living pantry section is the boulevard's most legible section because it is the section where the civilization's production function and the transit function are most directly collocated. The passenger in a standard intercity transit sees the geological formation, the limestone, the biological community, the halocline's optical anomaly, as evidence that the civilization exists inside a geological context whose nature it has committed to respecting. The passenger in a living pantry section sees the food system, the fish towers, the bioreactor columns, the harvest drones returning full, as evidence that the civilization has organized the geological context into productive use without removing it from view. Both are evidence of the same thing. The passenger in the living pantry section registers the evidence more immediately because the production infrastructure is immediately legible. A school of giant freshwater prawns in a suspended mesh cylinder is not ambiguous in the way a limestone passage wall is ambiguous. The prawns are food. The cylinder is a farm. The drone is harvesting. The civilization is eating from its own geology. This requires no interpretive framework the passenger does not already bring to the observation. The living pantry section is the boulevard's most communicative section because it communicates in a language everyone speaks. The Harvest Your Own Dinner programs that the Corridor Cenote installations offer, the evening aquaculture gallery visits where enrolled guests participate in the harvest drones assisted selection of their own meals protein, delivered to the Cenote Hub's restaurant gallery within an hour of harvest, begin their experience inside the transit tube. The guests' first encounter with the food they will eat that evening is through the crystal tube wall during the transit that brings them to the Corridor Cenote from the Formation Cenote where they are enrolled in the longevity program. The transparency of the production system is the transparency of the crystal tube wall. The wall was specified for geological observation and optical continuity with the formation. The production system was specified for aquaculture efficiency. The experience they together produce, seeing your food alive in its production environment from inside the transit system that connects the civilization's nodes, was not specified by anyone. It emerged from correct decisions made independently for separate reasons. This is the aquaforming doctrine's cultural output, not just infrastructure that fits the formation but a civilization whose most distinctive experiences are the products of design decisions that were not making cultural decisions. Wayfinding in the dark. The crystal tube network's intercity passages are dark outside the light relay's illumination cone. The light relay illuminates the transit zone ahead of the pod, the direction of travel is lit, the direction behind the pod is dark. The passage walls visible through the tube wall in the lit cone show the biological and geological character of that section of the route. The passage walls behind the pod, outside the lit cone, are the absolute darkness that has governed the cave since the Cenote network's formation. This is navigational darkness from the passenger's perspective only when the power systems fail. In normal operation, the coordinating system's pod location management provides real-time position data to the pod's navigation display. The pod knows where it is in the route at every moment. The display shows the distance to the next junction or destination, and the passenger who wants orientation information has it without looking at the passage walls. Wayfinding in normal operation is a data management task. The coordinating system manages it. In the blackout protocol, the total power failure scenario, the safety architecture is designed to manage without requiring power-dependent systems. Wayfinding reverts to the strontium illuminate rail markers, the passive glow elements embedded in the physical guide rail at standard intervals, emitting faint green phosphorescence that requires no power source, no electronic system, no communication with the coordinating system. The passenger in a blackout protocol scenario, pedaling the cycle sub's flywheel through absolute darkness with no light cannon relay and no coordinating system navigation display, follows the green line. The green line does not tell the passenger where they are. It tells the passenger where the rail is. Following the rail moves the passenger toward the nearest docking station, in whichever direction the passenger chose to pedal, at the speed the flywheel can sustain against the soda-lime CO2 scrubber's capacity. The wayfinding in a blackout protocol is not navigational, it is not finding a specific destination. It is finding any docking station, which provides atmospheric air replenishment, communication restoration, and access to the maintenance crew that the coordinating system will dispatch as soon as the power failure's extent and location are identified. The absence of location information in the blackout protocol is a design feature rather than a gap. Providing location information without the coordinating system's navigation layer would require an independent electronic infrastructure that is itself power dependent. The strontium illuminate markers require no power. Their information content, this is the rail, follow it, is exactly the information required to survive the blackout protocol. More information would not improve survival outcomes. Passive physical markers that work in the dark at zero power cost do the job the survival scenario requires. The green line is the boulevard's emergency typography. The coordinating system's navigation display is the boulevard's normal wayfinding. They are not two versions of the same system. They are two separate systems for two separate operational conditions, each chosen for what its condition requires rather than for coherence with the other. In normal conditions, the passenger is informed in real time by a system that knows exactly where they are and where they are going. In the blackout protocol, the passenger follows a phosphorescent trail in the dark. Both are correct for their condition. Acoustic character by depth. The boulevard sound changes with depth in ways the acoustic zoning protocol manages but does not fully control. The protocol manages the bypass vent tone frequency, the maintenance ultrasonic scheduling, the dolphin sonar management window, the human-generated and mechanically generated acoustic content of the passage network at each depth zone. It does not control the geological acoustic content, the formation's own sounds, transmitted through the limestone and the water column to the crystal tube's piezoelectric sensor network and thence, in filtered form, to the pod's interior audio environment. In the freshwater zone, the dominant geological acoustic input at most route sections is the underground river's flow signature, the broadband frequency content of turbulent water in constricted passage sections upstream of the route, transmitted through the water column at the speed of sound in freshwater. The character of this sound is dependent on the upstream passage geometry. A narrow constriction upstream produces a higher frequency turbulence signature than a wide passage transition. The coordinating system's acoustic monitoring network has characterized the turbulence signature at every route section, and the pod's interior audio presents it as the background against which the biological sounds, the low-frequency clicks and burst pulse vocalizations of the dolphin population in adjacent passages, filtered to the non-ultrasonic components that the acoustic zoning protocol passes through to the interior audio, are superimposed. At the halocline zone, the acoustic character changes. The temperature and salinity gradient that produces the optical dissolution effect also produces a change in acoustic impedance at the boundary, a partial reflection of acoustic energy propagating between the fresh and salt water masses. The reflections produce standing wave patterns at frequencies whose half-wavelength fits within the halocline zone's thickness. These standing wave patterns are the halocline's acoustic signature, as specific to the halocline as the optical dissolution is to the visual field, and as impossible to experience in any other environment. The pod's interior audio presents the standing wave pattern at the halocline zone, not as a musical element, not as an ambient sound design choice, but as what the coordinating system's monitoring records as the formation's acoustic behavior at that depth. The passenger hears the halocline. In the deep gallery sections, the saltwater zone tubes approaching the anoxic boundary, the acoustic character is the quietest in the network. The underground river's flow signature does not reach this depth. The freshwater flow is above the halocline, and the saltwater below the halocline moves at velocities too low to produce significant turbulence signature at the passage cross-sections the crystal tube traverses. The dolphin population's acoustic contribution is absent. The halocline is the biological lethal limit the dolphins cannot cross. The maintenance ultrasonic operations are scheduled away from transit windows. What remains is the geological acoustic baseline of the deep formation, the microseismic signal from the Chicxulub fracture network, the low-frequency resonance of the large chambers the route passes adjacent to, the almost inaudible subsonic pulse that the coordinating system's geological model attributes to the periodic pressure fluctuation in the anoxic zone's hydrogen sulfide chemistry as the microbial community's metabolic cycle produces pressure waves at the boundary between the anoxic sediment and the overlying saltwater column. The deep gallery's audio is the closest the civilization comes to the formation's own voice, the sounds the cave produced before any organism with ears inhabited it, before any manufactured acoustic event entered the passage network, before the crystal tube's bypass vents and the pod's propulsion added the sounds of habitation to the geological substrate. The coordinating system's filtering removes everything above the geological signal's frequency range from the deep gallery audio. What the passenger hears in the deep gallery transit is what the limestone sounded like when it was alone. This is not romantic. It is what the acoustic monitoring network captures when human and mechanical acoustic generation is subtracted. The formation's own acoustic signature, presented in the only environment where a human observer can be inside a tube at deep gallery depth to hear it. The transparency doctrine that put the passenger inside the formation to hear what the formation does extends to the acoustic dimension as automatically as it extends to the optical one. The boulevard hears what the formation says because the boulevard is inside the formation. The terminus and the threshold. Every intersynode transit ends at a hub, the cenote installation's central node where the crystal tube network connects to the cenote's internal gallery system and the surface tier's orientation platforms. The hub is the boulevard's terminus, the end of the intersynode route and the beginning of the destination cenote's internal navigation. The terminus is not a station in the surface world transit sense. There is no platform edge, no surface to disembark onto, no fare gate, no overhead announcement. The terminus is a docking port, the wetlock's conical alone reception disk, the mating sequence, the seal inflation, the vacuum dry pocket, the pressure equalization to ambient, the inner hatch opening. The hatch opening is the threshold event, the boundary between the inside of the transit pod and the inside of the destination cenote's inhabited space. The threshold is quiet. No ceremony. No announcement. The hatch opens, the pressure equalizes, and the passenger steps from the pod into the hub gallery with the biological and geological conditions of the destination cenote immediately present, the water visible through the hub's crystal walls at the hub's depth, the halocline at its current depth visible below or above depending on the route's arrival depth, the destination cenote's biological community's acoustic signature replacing the transit route's audio in the unmediated acoustic environment of the hub space. The arrival is sensory, not informational. The passenger does not learn they have arrived at the destination. They experience the destination's character through the transparency of the installation they have entered. If the destination cenote's biological community is denser than the originating cenotes, if the ecological maturity is greater, if the succession stage has advanced further, if the living pantry installation's aquaculture galleries are visible through the hub wall, the difference is immediately perceptible to the passenger who knows what the originating cenote looks and sounds like. The installation's character is in the sensory field, not in the signage. This is the Boulevard's final design decision, not to design the terminus as an information delivery event but to design it as a sensory event, trusting the civilization's transparent infrastructure to communicate the destination's character through the material the infrastructure is made of. The hub wall is crystal because the formation beyond it must remain visible. The formation beyond it is the destination. Arriving somewhere, in Pipe Dream, means seeing where you have arrived through the wall you are inside. The surface world's transit arrival is the announcement of arrival, the station name, the platform indicator, the map that shows you where you are. Pipe Dream's transit arrival is the perception of arrival, the destination cenote's formation, visible and audible through the transparent installation you have stepped into, telling you without words what the cenote is like and therefore where you have come. A civilization whose geography is legible through its own infrastructure has no need for the announcement. The wall tells you. The boulevard as epistemic commons. The transit between cenotes is the civilization's primary medium of collective knowledge about its own geography. Every passenger who makes an intercenote transit acquires direct sensory knowledge of the intercenote passage network, the biological communities of the route, the halocline's current depth, the light conditions at each depth zone, the geological character of the passage walls at each section. This knowledge is not delivered in a briefing or a document. It is acquired through the transparent tube wall, at boulevard speed, during a transit that the passenger made for a reason that had nothing to do with geological education. The coordinating system's passenger experience monitoring accumulates biosensor data from every occupied transit across the full network. The aggregate of this data is, from a different angle, the largest continuous human sensory perception dataset of an underground geological formation that has ever been generated. Not a survey. Not a scientific sampling campaign. A continuous record of what the civilization's inhabitants notice, attend to, and physiologically respond to as they move through their own geological substrate in a transparent enclosure at the speed designed for the experience to be legible. The coordinating system's ecological succession modeling incorporates this data, the spatial distribution of passenger visual attention, derived from biosensor data patterns that correlate with specific visual engagement states, across the route's passage sections tells the coordinating system which sections of the biological community are producing the highest passenger engagement. High engagement zones are zones where the biological community is producing visually distinctive conditions, dense colonization of a specific formation type, an unexpected species presence, a behavioral event in the cave fauna that the passive monitoring had not predicted from census data. The passenger who looked more intently at a specific passage section than at adjacent sections of similar geological character has told the coordinating system that something in that section warranted attention. The coordinating system does not know what the passenger saw. It knows where the attention was directed and for how long. It dispatches a biological census survey to that section before the next transit is scheduled. The census either confirms a biological community anomaly or establishes a baseline that the anomalous attention data will be compared against. Either way, the passenger's unexplained attention has generated a biological survey that the coordinating system's scheduled census program would not have produced at the same timing. The boulevard is a distributed sensing network for the coordinating system, not because the passengers are instruments, but because the passengers are organisms with perceptual systems sensitive to the biological community conditions the coordinating system's scheduled census cannot monitor at the spatial and temporal resolution that the continuous transit provides. The Terraform Operator Training Manual describes this relationship without framing it as surveillance. Passengers moving through the formation at boulevard speed, with biological attention directed freely at whatever the formation presents, provide the coordinating system with a spatial anomaly detection function that scheduled robotic survey cannot replicate. The boulevard is the civilization noticing its own geology. The coordinating system notes what the civilization notices. The terraform operators follow up. The formation's biological communities are monitored at the resolution the civilization's own attention provides. The epistemics of the underground boulevard are the epistemics of a civilization whose transit system is inside its own knowledge infrastructure. What the boulevard produces. A surface world boulevard produces commerce. The shops and cafes and kiosks that line it are there because the boulevard concentrates pedestrian traffic at a scale that makes commerce viable. The boulevard's economic function is inseparable from its transit function. The street is the market makes the street, the two are the same public realm in the same physical space. Pipe Dream's Crystal Tube Boulevard cannot produce commerce in this sense. The tube diameter does not accommodate retail. The transit speed does not accommodate stopping. The junction node is the only space in the intercity route where passenger circulation volume exceeds what the standard transit produces, and the junction node's throughput time is measured in minutes rather than in the dwell times that retail requires. What the boulevard produces instead is knowledge and encounter, the passenger's direct sensory knowledge of the formation's intercenote geography, and the brief junction node encounters between passengers from different origin cenotes that the transit sequence produces. These are not commercial products. They are not even intentional outcomes of the infrastructure's design. They are the accumulation of what happens when the civilization's sole medium of intercenote movement is a transparent enclosure passing through the formation at the speed that makes the formation legible. A civilization that knows its own geology through its own transit system is a civilization whose movement and whose knowledge are the same activity. The surface world separated these long ago, the transit system moves people, the knowledge institutions produce knowledge, and the two operate independently of each other. Pipe Dream's boulevard integrates them in the same infrastructure because the formation's transparency, maintained for engineering reasons, makes every transit an observation of the geology through which the transit passes. The boulevard is the civilization's university. Not because it was designed to teach. Because the transparent tube through geological space teaches by being what it is, what the formation's visual and biological and acoustic character teaches to any attentive observer who passes through it at a speed that makes the teaching legible. The curriculum is the formation. The classroom is the boulevard. The graduation is the 1,000-year design life in which the civilization's cumulative attention to its own geology, mediated by the transparent infrastructure it built to move through that geology, produced a knowledge base about the formation that no planned survey program, no scheduled census, no institutional research protocol could have generated alone. The formation taught the civilization. The boulevard is where the teaching happened. Cross-references, Part 2, CH1, Cities Made of Light, Part 2, CH4, The Crystal Tube Standard, Part 3, CH2, Mapping the Great Aquifer, Part 3, CH3, Linking cenote to cenote, Part 6, CH1, Pedal Submarines, Part 6, CH3, The Underground Safari, Part 7, CH5, The Blackout Protocol, Part 8, Section B, The Living Pantry. For pod speed parameters and boulevard versus functional transit mode differentiation, see Appendix D, Construction Operations Manual. For passenger experience monitoring biosensor protocol and coordinating system anomaly detection integration, see Appendix F, Biological Operations Manual. For junction node illumination configuration and social awareness parameter optimization, see Appendix D, Construction Operations Manual. Pipe Dream. Part 3, The Living Underworld. Chapter 5, Skyscrapers Beneath the Canopy. The Yucatan jungle does not know it is standing on a city. The ceiba trees whose roots penetrate the limestone to the water table do not know the water table is inhabited. The raptors that hunt from the canopy cannot see through the cenote openings to the luminous structures below them. The surface world, which defines the built environment as the collection of objects that interrupt the visual field of an observer standing on the Earth's surface, has no category for what exists in the cenotes of the Chicxulub arc, because what exists there does not interrupt any surface world visual field. The jungle is continuous. The canopy is unbroken. The city is underneath it, entirely, invisible to any observer who has not descended into it. The cenote hyperrise is the first tall building in the history of human construction that has no height from the outside. Standing at the cenote rim and looking across the jungle, the building is not there. Standing at the cenote rim and looking down into the opening, the building is there, lit, transparent, its structural columns descending from the surface tiers floating level to the deep gallery's chemostat boundary, its horizontal gallery rings connecting the columns at each depth tier, the biological community active on its exterior surfaces, the coordinating system's light relay making it luminous in the cave's otherwise absolute darkness. The building is present in its entirety from one specific vantage point, directly above it, looking down into the formation that contains it. From every other vantage point it does not exist. This is not the concealment of camouflage, a surface covered to resemble its background. It is the concealment of position. The building is inside the ground, and surfaces on the ground look at other surfaces on the ground, not at what is beneath their feet. The hyperrise concealment is geological rather than visual. It is in the wrong place to be seen by anything that looks at the world from the world's surface. The cenote opening is the only point from which it can be perceived, and the cenote opening is a hole in the ground. Part 2 documented what the hyperrise is made of and how it was built. Part 3 has documented the underground geography it occupies. Chapter 5's question is different from both. What does the hyperrise mean as a vertical presence in the living underworld, not as an engineering object and not as a geological occupant, but as a biological and metabolic fact in the cenote's three-dimensional ecology? The building is not installed into a neutral space. It is installed into a living system stratified by depth, temperature, chemistry, pressure, light availability, and the accumulated biological history of 66 million years of cenote evolution. The building does not interrupt this stratification. It participates in it. The cenote as vertical ecology. Before the hyperrise existed, the cenote's vertical axis was already the most information-dense dimension in the cave system's ecology. In the horizontal plane, a given depth in the cenote is relatively uniform. The water at 10 meters depth on the north side of the cenote is similar in temperature, chemistry, and biological community to the water at 10 meters depth on the south side. The horizontal variation is local and secondary, microhabitat variations produced by specific substrate textures, shadows from particular limestone formations, localized current patterns from specific fracture inputs. The vertical axis is the dimension of transformation. The first 10 meters, the freshwater zone's warm, sunlit, oxygenated upper column, sustains the photosynthetically active biological community, the algae and aquatic plants whose presence depends on light, the invertebrates whose feeding depends on the organic production the algae and plants generate, the fish species whose prey base depends on the invertebrates. The light field changes dramatically in this 10 meters, at the rim, full tropical sun for the direct illumination hours, at 5 meters, perhaps 20% of surface irradiance, at 10 meters, less than 5%. The biological community tracks this gradient, and the community composition at 10 meters is substantially different from the community at 2 meters, which is different from the community at the surface. At 15 meters, the halocline's approximate upper boundary under standard conditions, the transformation accelerates. The temperature drops multiple degrees over meters rather than over tens of meters. The salinity gradient begins, shifting from the freshwater zone's essentially zero salinity to the saltwater zone's full Caribbean salinity across a boundary that is geometrically thin but ecologically absolute. The biological community that lives above the halocline cannot cross it downward. The salinity shock and the H2S that increases rapidly below the halocline represent lethal conditions for the freshwater species that have evolved for the upper column. The biological community below the halocline cannot cross it upward for the same reason in reverse. The halocline is a hard biological boundary, as effective as any physical wall, maintained not by any structure but by the chemistry of two water masses coexisting at contact without mixing. Below the halocline, the transformation continues along the anoxic gradient. Dissolved oxygen decreases from the saltwater zone's modest concentration toward zero as depth increases. H2S increases in the opposite direction. The biological community transitions from the aerobic organisms of the saltwater zone, adapted for low oxygen, high salinity conditions, but still aerobic, through a microzone where anaerobic bacteria coexist with the last aerobic organisms whose tolerance for H2S and oxygen depletion extends furthest, to the pure anaerobic community of the deep anoxic zone where dissolved oxygen has been absent for so long that the geological record holds no memory of it having been present. The cenote's vertical axis, in 66 million years of biological succession under these conditions, has produced a stratified ecology whose vertical organization is among the most precisely constrained in any aquatic environment on the planet. Each depth has its biological community. Each community exists at its depth because the chemical and physical conditions at that depth are the conditions that particular community's evolutionary history has equipped it to exploit. The vertical organization is not a design. It is the accumulation of 66 million years of chemical gradient interacting with biological evolution. The hyperrise is installed in the cenote's vertical axis. It does not flatten the gradient. It does not mix the zones. It extends through all three of the cenote's ecological zones, from the surface tier at the freshwater zone's light-active upper column to the deep gallery at the anoxic boundary, and in doing so, it occupies the full range of the cenote's ecological conditions within a single building. No surface world building occupies this range of ecological conditions. No surface world building passes through a hard biological boundary on its way from the ground floor to the basement. No surface world building has its upper floors in sunlight and its lower floors in a zone of absolute darkness, hydrogen sulfide chemistry, and extremophile microbial ecology. The hyperrise is not a building that happens to be underground. It is a building whose entire vertical organization is determined by the ecological stratification of the underground environment it occupies. Each floor of the hyperrise is at a specific depth. Each depth has a specific set of ecological conditions. Each set of ecological conditions determines the human biology protocols appropriate for habitation at that depth, the atmospheric mix, the pressure, the therapeutic exposure parameters of the longevity program. The building's social and medical topology is the ecological gradients topology, organized for human habitation. The crown, food forest and canopy. The hyperrise presence in the cenote does not terminate at the water surface. The founding module at the surface tier is not the building's top floor. The food forest on the cenote rim is the building's crown, the agricultural and ecological superstructure that receives the resource outputs of the installation below and produces the food and biological material that flow back down. The cenote rim's food forest is not a garden. It is a managed ecological succession at a specific succession stage, a polyculture of native dry tropical forest species selected for food production, canopy architecture compatibility with the cenote's light requirements, root system compatibility with the limestone substrate, and mycorrhizal partnership capacity with the soil fungal networks the mycofiltration panel harvests support. The succession stage is managed by the terraform operators, who conduct quarterly biomass surveys and coordinate with the coordinating system's carbon flux model to maintain canopy density at the level that permits the morning sun column through the cenote opening while preventing evaporative water level loss from excessive air exchange. The food forest receives the ballast overflow, the filtered water discharged from the installation's ballast circuit on the diurnal and seasonal cycles that match the forest's uptake capacity. It receives the black water digestate, the liquid fraction from the anaerobic digestion of the installation's black water stream, stripped of pathogen load, applied to the irrigation header on the schedule the forest's seasonal growth cycle determines. It receives the mycofiltration panel harvest, the fungal biomass produced monthly by the gray water processing gallery's mycelium panels, applied as soil amendment to the forest floor where the mycorrhizal network's expansion is most needed. The food forest does not receive these inputs because they are waste products the installation needs to dispose of. It receives them because the installation was designed as a closed loop and the food forest's biological function is to process the loop's output streams. The ballast overflow is not sewage, it is filtered water with a dissolved mineral load that the food forest's calcium-demanding limestone-adapted species process as nutrition. The black water digestate is not effluent, it is the nitrogen-rich liquid fraction of the organic matter the installation's inhabitants generated, transformed by anaerobic digestion into a form the forest's root systems can absorb directly. The mycofiltration harvest is not waste biomass, it is the fungal material whose network the food forest soil requires to maintain the nutrient transfer efficiency that makes the forest increasingly productive with each year of ecological maturation. The food forest is the installation's longest cycle biological system. The Ancistrus vitreous colonies reproduce on weeks to months timescales. The lithocrustacean boring colony advances on days to weeks timescales. The food forest's ecological maturation advances on years to decades timescales, the mycorrhizal network's expansion through the forest substrate, the canopy species growth to the height at which their shade management function operates correctly, the soil's organic matter accumulation to the depth at which its water retention capacity reduces the irrigation requirement to the minimum the ballast overflow provides. A food forest managed for a year is a young food forest with most of its productivity unrealized. A food forest managed for 30 years is a forest whose yield per unit of resource input is higher than in year one because the biological capital, the mycorrhizal network, the soil community, the canopy architecture, has had 30 years to develop. The food forest crown is also the hyperrized thermal management's external expression. The cenote's air exchange with the surface atmosphere occurs through the cenote opening. The food forest's canopy manages the humidity and temperature of the air immediately above this opening, moderating the temperature of the air column that descends through the opening to the surface tier, reducing the thermal load the surface tier's ballast system must manage on hot dry season afternoons, and maintaining the moisture gradient that prevents the evaporative water loss that a dry, hot surface atmosphere in direct contact with the cenote's freshwater surface would produce. The food forest is not designed as thermal infrastructure. It was specified for food production, soil amendment reception, and canopy management. The thermal management function is a byproduct of the canopy architecture that the food production species achieve at their mature height. The correct canopy for food production is also the correct canopy for thermal management. Once again, the same design decision, made for one reason, produces multiple correct outcomes. The building as metabolic section. Standing inside the founding module's lowest surface tier gallery and looking downward through the translucent floor, looking through multiple tiers of the hyperrized descending structure, through the halocline's optical dissolution effect visible at depth through the transparent columns, toward the dim bioluminescent glow that the coordinating system's biological monitoring network picks up from the anoxic zone's microbial community below, the observer is not looking at floors. They are looking at a cross-section of the cenote's entire metabolic system, organized into inhabited geometry. The surface tier, the observer's floor, is where the civilization's energy inputs are highest. The light relay originates here from the strongest available illumination source. The food forest's biological productivity, which the ballast loop feeds from the surface tier's organic outputs, peaks at the canopy's solar energy input. The tourism program's arrivals are here, the first point of contact between the surface world and the civilization, where the energy and economic input the tourism program generates enters the installation. The surface tier is the civilization's high-energy zone, maximum solar energy, maximum economic throughput, maximum guest density, maximum biological productivity in the freshwater zone's photosynthetic community. Below the surface tier, descending through the freshwater zone's gallery rings, the energy input decreases and the therapeutic function increases. The longevity program's primary operating environment, the pressure gradually increasing, the light field transitioning from the surface tier's direct solar column to the light relay's transmitted luminosity, the biological community shifting from the photosynthetically active surface community to the depth-adapted species of the mid-freshwater column. The nitrox galleries, enriched oxygen-breathing gas at therapeutic partial pressure, the atmospheric management system delivering dialed mixtures to each gallery's guest population at the depth and pressure appropriate to each guest's individual protocol. The energy input here is the foundation of the civilization's medical program: atmospheric pressure and oxygen partial pressure, applied continuously to a resident population whose biological response the coordinating system's weekly bloodwork monitoring tracks. At the halocline, the zone transition that the hyperized structure crosses and that Part 2 documented in engineering terms as the thermal management problem, the refractive index transition problem, the biological boundary management problem, the building passes through the cenote's most ecologically significant boundary. The halocline is where the two water masses that make the cenote's energy architecture possible meet: the freshwater above, continuously recharged by jungle rainfall and maintaining the oxygenated zone the hydrodynamics require; the saltwater below, pushed from the Caribbean through the limestone's fracture network by the oceanic hydraulic gradient, maintaining the deep zone's chemistry and enabling the halocline's electrochemical harvest potential. The building structure at the halocline is not crossing a boundary between two floors. It is crossing the boundary between two geological systems that happen to coexist in the same cenote at contact. The saltwater zone below the halocline is the civilization's medium pressure zone. The permanent residents who work at depth, the researchers, the deep gallery terraform operators, the governance staff whose roles require proximity to the intelligence layer, inhabit this zone at pressures between 1.4 and 2.0 atmospheres. The therapeutic pressure rationale of the longevity program extends into this zone. The permanent residents who have been in continuous hyperbaric exposure for years rather than the months of the guest program have bloodwork profiles that the coordinating system's research database tracks as the most longitudinally extensive hyperbaric biology dataset in existence. They are not experimental subjects. They chose depth. Their biology has been responding to depth since their residency began. The response is what the research database is building. The deep gallery, the hyperized lowest inhabited levels, at the anoxic boundary, is not habitation in the surface world sense. No one sleeps here on the first night and wakes up adapted. The deep gallery's permanent residents are the terraform operators who have completed their full-season supervised residency in the anoxic zone's monitoring protocols and accepted permanent assignment to the gallery that operates at the chemostat interface. They are the civilization's deepest workers, not in hierarchy, not in status, but in the literal sense of physical depth. They are at the building's lowest occupied level, at the highest pressure, at the closest proximity to the biological system that drives the civilization's industrial metabolism. The view from the deep gallery upward, through the successive tier levels of the hyperrise, through the haloclines blurring at the mid-building boundary, through the freshwater zone's increasingly lit column toward the surface tier's full illumination, is the civilization's metabolic gradient made visible. The deep gallery terraform operator looking upward through the transparent structure sees the full vertical extent of what the civilization is: the food system and energy inputs at the top, the therapeutic pressure program in the middle, the governance and intelligence infrastructure at the deep, and the chemostat's industrial metabolism at the bottom of everything, below the lowest gallery, where the extremophile community that has been operating in absolute darkness since before the Maya arrived continues its geological timescale chemistry indifferent to the inhabited structure above it. The building is a cross-section of the civilization's metabolism. Every floor level is a metabolic function. The vertical sequence is the metabolic logic. The deep gallery's bioluminescence. The anoxic zone below the hyperized deepest inhabited gallery is not dark in the absolute sense that the surface world's understanding of underground darkness implies. It is dark in the sense that no photon from any surface or engineered light source reaches it. The light relay's projection does not penetrate the halocline, and even if it did, it would be absorbed within meters of entering the anoxic zone's hydrogen sulfide-rich water. The anoxic zone's darkness is the absence of light energy from outside. But it is not silent in the electromagnetic sense. The extremophile microbial community that the chemostat chapter, part 10, documents in full metabolic detail produces bioluminescent emission, low-intensity, biologically specific wavelengths generated by the luciferase equivalent enzymatic reactions in the anaerobic bacteria and archaea that constitute the dominant community. The emission is not visual illumination in any useful sense. It does not light the anoxic zone. It is the metabolic byproduct of chemical reactions that happen to release energy at visible wavelengths as part of their thermodynamic cycle. The bacteria are not producing light to be seen. They are producing light because the chemistry of their metabolism releases photons. The alone structural panels of the deep gallery, specified for their hydrogen sulfide resistance and their optical transmission across the midwave infrared range at which the coordinating system's H2S monitoring operates, also transmit the visible wavelengths at which the microbial community's bioluminescent emission occurs. The deep gallery's outer wall, which faces the anoxic zone, transmits the microbial community's bioluminescent output into the gallery interior in the same way the surface tier's walls transmit the cenote's daylight column. What the deep gallery terraform operator sees through the alone wall into the anoxic zone is not darkness. It is darkness punctuated by the diffuse, shifting, biologically specific glow of a microbial community that has been producing this light for longer than the Yucatan has had surface mammals. The glow is faint. The coordinating system's biological census cameras require high sensitivity enhancement to image the community in the conditions the bioluminescent emission provides. The unaided human eye at the alone wall sees the glow as an ambient luminosity in the dark zone, not as distinct sources, not as a pattern, but as the visual evidence that something biological is happening in the absolute darkness beyond the wall. The Deep Gallery's interior lighting protocol is designed around this. The gallery's engineered lighting is maintained at a low level during the standard observation periods when terraform operators are working at the alone wall interface, low enough that the bioluminescent emission from the anoxic zone remains visible through the wall. The alone panel, which was specified for chemical resistance and infrared optical transmission, provides the viewing window through which the civilization's deepest permanent residents observe the biological system that Pipe Dream calls its most ancient partner. Not by design. By physics. The correct material for the correct reasons transmits the correct light. The observation of the bioluminescent community through the alone wall is not a scheduled activity in the terraform operator's workday. It is what happens when a terraform operator is working at the Deep Gallery's alone wall interface on the H2S monitoring protocol, chemical harvest schedule management, or chemostat cycle prediction consultation, and looks up from the sensor display at the wall. The microbial community is always there, always glowing, always doing the chemistry it has been doing for geological time, visible through the wall the terraform operator is standing next to for entirely different operational reasons. The Deep Gallery terraform operator who has been at depth for a full season develops a sensory familiarity with the bioluminescent field that the coordinating system's monitoring instruments do not develop, a pattern recognition, not articulated, not documented, not formalized, for when the glow is doing something different from its normal temporal pattern. An intensity shift. A spatial distribution change. A spectral character that feels different from the baseline. The terraform operator who notices this files a chemostat anomaly report, which triggers the coordinating system's expanded monitoring protocol at the anoxic boundary, which either confirms an anomaly in the microbial community's chemistry or establishes a baseline against which the unusual pattern will be compared in subsequent monitoring cycles. The terraform operator's unaided visual perception through the alone wall is the chemostat's early warning system. Not because it was designed as one. Because the correct material, correctly specified for engineering reasons, is transparent to the light the biological system produces, and the human visual system can detect changes in that light before the coordinating system's spectroscopic monitoring identifies them as anomalies in quantitative terms. The observation window that H2S chemical resistance required is also the biological monitoring interface that the terraform operator's sensory perception provides. The canopy relationship. The jungle canopy above the cenote opening and the hyperrise below it are not in the same ecological system. The canopy is a tropical dry forest ecosystem, its biological community organized around rainfall seasonality, solar energy, the nutrient cycles that the leaf litter and decomposition processes drive. The hyperrise is an underground freshwater ecosystem, its biological community organized around hydrological chemistry, pressure stratification, the organic inputs that the underground river system delivers from the jungle soil water as rainwater passes through the karst. They are different systems. They have different species, different energy inputs, different cycle timescales. They are connected through the cenote opening in ways that run in both directions. The jungle sends the hyperrise, rainwater that becomes the ballast system's primary input, dissolved organic matter in the soil water that enters the aquifer as recharge and delivers the nutrient load the cave's biological community depends on, organic debris, leaves, insects, pollen, fungal spores, that enters the cenote through the opening and descends through the water column to the sediment communities that process it, the roots of the food forest's canopy species, which penetrate the limestone to the water table and draw the installation's ballast overflow and black water digestate back upward in the soil water column that feeds their growth. The hyperrise sends the jungle, the heat that the Deep Gallery's compute infrastructure produces and that the thermal management system dissipates into the limestone sink and thence to the soil and the root zone, the carbon dioxide that the installation's inhabited levels produce through respiration and that the surface tier ventilation exhaust adds to the cenote opening's air exchange with the jungle's atmosphere, the water that the food forest's irrigation receives, which is ultimately the ballast overflow and black water digestate that the installation's occupants' metabolism produced, and, through the food forest's root mycorrhizal network, the phosphorus and trace mineral nutrition that the mycofiltration panel harvests release into the soil when applied as amendment. The exchange between the hyperrise and the canopy above it is the closing of a nutrient loop that the surface world's waste management systems close imperfectly through treatment plants, landfills, and atmospheric emission. In Pipe Dream's installation, the loop closes through the limestone, the same limestone that makes the aquifer, provides the cenote opening, produces the halocline's mineral chemistry, and receives the food forest's root system. The building's metabolic outputs return to the formation through the formation's own biological systems. The loop has no exit because the formation is both the input and the output. The canopy does not know it is the top floor of the building below it. The ceiba tree whose roots reach the water table and absorb the ballast overflow does not know it is performing the final step in the ballast loop. The mycorrhizal network in the food forest soil does not know it is processing the mycofiltration harvest as part of an engineered closed-loop system. The ecology performs the function because the ecology's biology equips it for the function, and the function's design placed the correct biology in the correct position in the nutrient cycle. Aquaforming at the food forest level means, put the nutrients where the forest wants them, put the forest where the nutrients come from, and the forest will do the rest. The forest has been doing the rest for the 30 years the founding installation's food forest has been managed. It is better at it every year. The hyperise as geological instrument. The hyperise structural columns, the chemically strengthened aluminosilicate glass elements whose crazing failure signature Chapter 2 established as the civilization's most widely distributed structural health monitoring system, are also acoustic instruments in the cenote's geological monitoring architecture. The limestone transmits seismic signals through the cenote walls to the water column and from the water column to any structure in contact with the water. The hyperise anchor pylons, the telescoping stainless steel and Inconel elements that connect the founding module and each subsequent tier to the cenote wall's limestone, are in direct mechanical contact with the formation. Every microseismic event in the Chicxulub fracture network that produces a stress wave through the limestone reaches the hyperise through the anchor pylon interface. The piezoelectric sensors in the borosilicate carbon composite transit tube sections receive the same signal from the water column that transmits it from the limestone to the water. The hyperise, as a result, is not only a structure that the coordinating system monitors for structural condition. It is a seismometer, a large-scale mechanical detector for the formation's geological activity, whose multiple anchor points at multiple depths provide the spatial sampling that allows the coordinating system's geological model to locate microseismic events in 3 dimensions from the differential arrival times at the anchor sensors. A building that tells the formation what is happening in the formation is a building that is doing geological work as a byproduct of being anchored. The anchor pylons were specified to connect the building to the limestone structurally. The geological monitoring function is what structural connection to the limestone produces when the limestone is geologically active and the connection interface carries the mechanical signal to the sensor network. The foundation is the seismometer. The hyperise deepest anchor points, the Inconel pylons at anoxic zone depths, are the geological monitoring network's most sensitive sensors for the Chicxulub fracture network's deep zone activity. The deep limestone seismic signature reaches these sensors before it reaches the surface zone anchors, because the fracture zone is at depth and the signal propagates upward. The deep anchor data arrives at the coordinating system's geological model before the surface anchor data from the same event. The depth sequence of arrival times is the 3-dimensional location of the event's source. The hyperise is a tall building whose foundations are distributed across 3 geological zones and whose structural monitoring network is the formation seismograph. Neither function was designed to produce the other. Both are what happens when the building and the formation are correctly connected, monitored continuously, and interpreted by a coordinating system that treats every sensor reading as potentially relevant to multiple concurrent analytical questions simultaneously. What the building looks like from the rim. The observer standing at the cenote rim looking down into the opening sees the light before they see the building. The light cannon relay's illumination rises from below, from the surface tier's light relay arrays projecting downward into the hyperise interior and outward through the translucent walls into the cenote water surrounding the structure, and the combined illumination produces, at the cenote rim, an upwelling glow visible before the structure itself resolves. The cenote opening looks lit from below. Not sunlit, the color, temperature and directionality are wrong for sunlight. Lit from within, from a source in the cenote that is illuminating the cenote walls and the water column surrounding the structure. As the observer's eyes adjust to the contrast between the jungle's ambient illumination and the cenote opening's lit interior, the structure resolves. The crystal columns, vertical, catching the light at their surfaces in the way that glass catches light, not absorbing it but bending it slightly at the surface, producing a bright edge that reveals the column's presence by the light it refracts rather than the light it blocks. The horizontal gallery rings, visible as slight density changes in the visual field at the depths where they occur, the accumulation of the structural elements at each tier level visible as a subtle darkening of the transparent field at the gallery floors. The biological community on the exterior surfaces, the Ancestris vitreous colonies semi-translucent and in motion, the sessile invertebrates that have colonized the anchor bracket faces, the biofilm communities on the surfaces between cleaning cycles, visible as texture on the otherwise clear structural elements. The building is there. It is not hidden. Looking directly down into the cenote from the rim, in the upwelling light of the relay, the entire structure is visible, the surface tier's circular footprint matching the cenote's approximate circular opening, the descending column structure narrowing toward the depth zones where the cenote walls converge, the halicline's optical dissolution visible as a blurring stratum somewhere below the freshwater zone's clearly resolved structure, and below the halicline the darkening and the diffuse bioluminescent glow of the deep gallery's alone panels transmitting the anoxic zone's microbial light. The building is present. It is taller than most surface world tall buildings, measured from the food forest canopy above the rim to the deepest alone gallery at the anoxic boundary. The vertical extent of the full installation exceeds what any standard architectural measure of height captures because the standard measure runs upward from the ground and the hyperise runs in both directions from the ground simultaneously. What the surface world would call the height, the extent above the cenote rim, is the food forest canopy's 15 meters. What the surface world would not measure at all, the extent below the cenote rim, is the distance from the water surface to the anoxic boundary's deepest gallery, potentially 70 to 100 meters or more in a formation cenote of sufficient depth. The hyperrise is simultaneously the shortest tall building in the surface world's frame of reference and the tallest building in the formation's frame of reference. The surface world's frame of reference measures height upward from the ground. The formation's frame of reference measures depth downward from the water surface. In the surface world's measure, the hyperrise barely registers. In the formation's measure, the hyperrise extends through the full vertical range of the cenote's ecology, from the photosynthetically active surface to the geologically ancient deep. The correct measure is the formation's measure. The building is inside the formation. It is measured by the formation's dimensions. The canopy view from above. An aerial observer, a drone at canopy altitude, or the heavy lift unit during a construction sortie, sees the cenote network in the surface world's frame, jungle, cenote openings as circular interruptions in the canopy, no building visible from above. The circles of canopy break are the only evidence from this altitude that the formation below contains anything other than undifferentiated limestone and water. From the right angle and altitude in good light, through a cenote opening large enough to allow the observation, the aerial observer can resolve the upwelling glow that the surface tier observer at the rim sees from close range. The glow at altitude is a faint illumination of the cenote opening, the cenote circle in the canopy looking lit rather than dark when the interior light relay is active. An experienced observer who knows what to look for will identify the illuminated circle as something other than a standard cenote opening catching reflected sky light. An observer who does not know what to look for will see what the jungle presents, a circular gap in the canopy with an unusually lit interior. No structure. No building. No evidence of habitation visible from the air. The civilization's invisibility from altitude is not a security protocol. It is the consequence of building inside the formation rather than on top of it. The formation does not advertise the civilization. The canopy does not advertise the cenote openings. The aerial observer who finds the illuminated cenote circles interesting has found, by looking at the surface world from above at the right moment in the light relay's operating cycle, the only aerial evidence that the formation contains something worth investigating. Investigation requires descent. Descent leads to the cenote rim. The cenote rim leads to the look downward into the upwelling light. The look downward resolves the structure. The structure's invitation is the hatch of the first cycle sub in the orientation sub pool at the surface tier's arrival platform. The arrival is the beginning of the descent through the ecology, through the freshwater zone's biological community, through the halocline's optical anomaly, through the saltwater zone's therapeutic pressure, to whatever depth the guest's protocol or the terraform operator's assignment places them. The civilization discloses itself to the descent. The surface world, which builds its cities to be seen from a distance, which measures prestige and skyline prominence and architectural visibility, which orients its buildings toward views and natural light and the acknowledgement of adjacent observers, the surface world cannot find pipe dream by looking. It can only find pipe dream by going down. This is not a defensive posture. It is a geological one. The civilization is inside the ground because the ground is where the formation is. The formation is where the civilization was built. The civilization is not visible from the surface because it did not build on the surface. The surface remained the surface. The jungle remained the jungle. The canopy remained unbroken. And below the canopy, in the upwelling light of the relay, in the thermal management of the food forest's crown, in the acoustic signal of the anchor pylon's seismic sensors, in the bioluminescent glow visible through the alone panels from the deep gallery, the civilization is there, 100 meters tall in the measure that matters, invisible to every frame of reference except the one that the formation provides. The cenote is the vantage point. The formation is the reference frame. Everything else, the surface world's maps, the host state's cadastral surveys, the aerial cartography that shows the Yucatan as undifferentiated jungle interrupted by cenote circles, is looking at the wrong dimension. The view from inside. The question that matters most to the civilization is not what the hyperrise looks like from the rim. It is what the cenote looks like from inside the hyperrise. The building was not built for observers outside it. It was built for inhabitants inside it. From the surface tier, the orientation galleries and arrival platforms at the freshwater zone's illuminated upper level, the cenote is fully present. The crystal walls show the cenote volume in all directions, the cave ceiling formations above, accessible at the cenote rim by the food forest's edge, the cave walls curving inward or outward depending on the cenote's specific dissolution geometry, sometimes close enough to read individual mineral compositions in the limestone, sometimes far enough to require the light relay's illumination to resolve, the water column below the surface tier's floor level, descending through the visible freshwater zone to the halocline's blurring boundary and the depth beyond it. The surface tier occupant is in a transparent enclosure inside a cave. Both the enclosure and the cave are simultaneously present. Neither has priority in the visual field. From the longevity program's mid-depth galleries, Below the surface tier's direct light column, in the pressurized nitrox atmosphere of the therapeutic zone, the cenote's visual character is different. The light relay's transmitted illumination provides the primary light source. The color temperature is different from daylight. The laser diode spectral composition differs from solar spectrum in ways the coordinating system's relay programming partially compensates for through spectral mixing, but the full solar spectrum's daily variation is not present at depth. The light is consistent. It does not have the morning's blue-shifted quality or the afternoon's warm directional quality or the diffused overcast light that clouds produce at the cenote rim. It is the light the relay provides, at the intensity the coordinating system sets for the depth zone's therapeutic protocol, consistent across weather and time of day. The cenote visible through the mid-depth gallery walls has a different biological character than the surface tiers. The photosynthetically active surface community is above, its zone boundary visible through the transparent floor where the light field and biological density drop at the surface tier's lower boundary. The mid-depth column's biological community is adapted to lower light and the beginning of the pressure gradient, different species, lower overall density, more concentrated at the wall surfaces where the substrate and the biological community's maintenance cleaning have produced the stable colonization base that the open water column at depth does not support. The helicline is visible from the mid-depth galleries as a depth horizon below, not a sharp line but the zone where the visual field loses resolution, where the optical dissolution effect begins to assert itself over the crisp transparency of the freshwater column above. For guests enrolled in the longevity program at depths approaching the helicline, this visual horizon is a constant presence in the peripheral field, the formation's reminder that the boundary between two geological systems is within the visual field, below the floor level, present in the same cenote that the therapeutic pressure and the nitrox atmosphere and the weekly blood work are happening inside. From the deep gallery, the alone-paneled galleries at the anoxic boundary, the cenote visible through the wall is not the cenote of the surface world's understanding. It is the cenote's deep interior, the saltwater zone's extreme darkness except for the biological monitoring network's discrete sensor lights, the settling particulate of the annual organic debris accumulation that the underground river system delivers from the jungle above, the absolute dark below where the alone panel's midwave infrared transmission shows the coordinating system's monitoring instruments, the anoxic zone's chemistry, and the biological monitoring shows the bioluminescent microbial communities glow to the terraform operator's unaided eye. The deep gallery cenote is not the cenote that the tourist orientation video describes. It is the cenote that the formation has been building for 66 million years, the cenote's purpose, in the geological sense, not the light column and the biological spectacle of the freshwater zone, but the chemical reactor of the anoxic depth, where the organic matter that has been raining down through the water column since before humans existed is processed by the microbial community into the mineral and chemical outputs that the chemostat manages as the civilization's industrial metabolism. The tourist arriving at the surface tier and looking at the cenote through the crystal wall sees the photogenic, illuminated, biologically vivid freshwater zone, the cenote the surface world has always associated with the Yucatan. The terraform operator at the deep gallery looking through the alone panels into the bioluminescent dark sees the cenote the surface world has never seen and has no framework to understand, the cenote's basement, its engine room, the biological system that makes everything above it possible by processing 66 million years of accumulated organic matter into the mineral outputs the civilization has organized as industrial production. Both observers are inside the same building. They are inside different centuries of the same cenote. The hyperrise holds them both, the tourist cenote and the terraform operator cenote, in the same vertical extent, connected by the transparent columns that pass from one to the other, visible to each from the other's depth as a glow above or a darkness below, both present, both necessary, neither comprehensible without the other. The building is the bridge between the cenote's two faces. The surface face, accessible, illuminated, biologically exuberant, that the surface world has always been able to descend to and return from. And the deep face, inaccessible, dark, biologically ancient, chemically specific, that no surface organism has ever inhabited until Pipe Dream descended into it and stayed. The hyperrise is both at once. That is what makes it a civilization rather than a dive site. Cross-references, Part 1, CH4, Floating Before Anchoring, Part 2, CH1, Cities Made of Light, Part 2, CH2, Engineering Invisible Architecture, Part 3, CH1, Rivers Beneath the Jungle, Part 4, CH6, Biological Civil Engineering, Part 5, CH6, Ecology as Infrastructure, Part 10, CH2, The Chemostat, Part 11, CH1, Living Under Pressure, Part 11, CH2, The Nitrox Galleries. For food forest species selection protocol and quarterly biomass survey methodology, see Appendix F, Biological Operations Manual. For deep gallery alone panel bioluminescent observation protocol and chemostat anomaly reporting format, see Appendix G, Formation Intelligence Record. For anchor pylon seismic monitoring integration and microseismic event location calculation methodology, see Appendix A, Formation Baseline Protocol. Chapter 6, The First Regional Network. A regional network is not a collection of installations. The distinction is the same distinction that separates a city from a collection of buildings, a language from a collection of words, an ecology from a collection of organisms. The collection has components. The network has properties that none of its components possess individually, properties that emerge from the connections between components rather than from any component's intrinsic character. These emergent properties are not additive. They do not appear when enough components are assembled. They appear when the connections between components reach the density and quality at which the network begins to behave as an entity whose capabilities exceed the aggregate of what its components could do in isolation. Pipedream becomes a regional network at a specific moment in its development. Not when the second cenote is connected to the first. Not when the third cenote is connected to the second. The threshold is behavioral rather than numerical, the moment when the coordinating system's formation model for any individual cenote is improved more by sensor data arriving from other cenotes through the crystal tube network than by new sensor data from within the cenote itself. When this happens, when the external network's contribution to local intelligence exceeds the local contribution, the installation has crossed from being a node with connections to being a node in a network. The network is a different kind of entity from the nodes that constitute it. This threshold has a specific implication for the coordinating system's architecture that was built into the digital twin's design from the founding installation's first operational day, in anticipation of the moment when it would become relevant. The formation model is not a cenote model. It has always been an aquifer model, a model of the great aquifer's behavior across the full extent of the passage network the coordinating system has observation data for. Individual cenote sensors are inputs to this model. The model's outputs are available to every cenote installation that contributes to it. The architecture was designed for the regional network before the regional network existed, because the founding engineers understood that the formation does not organize itself around individual cenotes and neither should the intelligence system that models it. What the network knows. The digital twin's aquifer layer, at the moment the first regional network threshold is crossed, contains formation data from multiple cenote installations and from the inter-cenote passage zones connecting them. The data density, sensors per unit volume of formation, is highest at the cenote hubs, where the crystal tube network sensor infrastructure is most concentrated, and decreases through the inter-cenote connection zones toward the regions ahead of the boring program's advancing fronts, where only the transceiver chain's forward detection data and the passive acoustic analysis's hypotheses exist. This spatial data distribution produces a formation model with a specific uncertainty topology, well constrained at the nodes, increasingly uncertain between nodes, and hypothesis level beyond the network's current extent. The model's spatial uncertainty topology is also the civilization's knowledge topology, what it knows well, what it knows approximately, and what it suspects but has not confirmed. The uncertainty topology is rendered in the coordinating system's display as a continuous confidence gradient, the same visual representation that the aquifer layer has maintained since the founding installation's first sensor reading, now spanning a regional geographic extent rather than a single cenote. What the network knows that no individual cenote could know. The regional halocline behavior. The halocline is not a local feature. It is the surface between two aquifer-scale water masses, the freshwater lens that the peninsula's rainfall maintains above, and the Caribbean saltwater that the oceanic hydraulic gradient pushes up through the limestone fracture network from below. The halocline's depth at any individual cenote is the local expression of a regional pressure balance between these two masses. A single cenote's halocline sensor measures a point on this regional surface. Multiple cenotes' halocline sensors, distributed across the Chicxulub arc's geographic extent, measure the regional surface's shape, its tilt, its seasonal deformation, the way a major rainfall event depresses it inland while a dry period allows it to rise. The regional halocline model that the network produces is the first time the freshwater/saltwater boundaries' three-dimensional behavior across the peninsula's aquifer has been observed continuously, in real time, by a permanent sensor array rather than by periodic diving surveys at individual cenotes. The regional flow distribution. The underground river system's flow distribution across the passage network, which passages carry the highest flow velocities during wet season high recharge conditions, which lateral passages are backflow zones during dry season low gradient conditions, how a major rainfall event in the inland recharge zone propagates as a pressure wave through the passage network toward the coast, is visible as a network phenomenon only when sensors at multiple nodes detect the propagating signal. A single cenote's flow velocity sensors measure the signal at one point. The network's distributed sensors measure the signal's propagation speed, attenuation, and directional character across the regional passage geometry. The coordinating system's regional flow model derives the passage network's hydraulic conductivity distribution from this data, the hydraulic map of which passages carry flow efficiently and which impose resistance, more accurately than any surface hydrogeological survey has achieved for any comparable karst system. The regional geological stability. The Chicxulub fracture network's microseismic activity, the continuous low-level geological background that Chapter 5 documented as detectable at individual anchor pylon seismometers, is a regional phenomenon. Microseismic events in the fracture network propagate outward from their source through the limestone and water at speeds the multi-node sensor array can use to triangulate source location in 3 dimensions. A single cenote's anchor sensors detect the event's arrival. The network's distributed anchor sensors detect the differential arrival times at multiple nodes, and the coordinating system's geological model inverts the differential timing to locate the event's source in 3 dimensions with a spatial resolution that the single cenote measurement cannot approach. The regional geological stability model shows not just that microseismic activity is occurring but where it is occurring, at what depth, along which fracture orientations, and with what temporal clustering pattern. The pattern is the formation telling the coordinating system where stress is accumulating in the fracture network, where the next collar event is statistically most likely to occur, and therefore where the boring program's advance should slow and the crystal tube inspection frequency should increase. The regional ecology. The biological corridor management protocol that Chapter 3 documented for the bilateral cenote connection, the freshwater zone's pink dolphin population's behavioral deterrent management, the Ancestris vitreous colonies cross-cenote transport risk, the pre-transit biological inspection protocol, extends to a regional corridor management challenge when the network's freshwater zones are connected across multiple cenotes. What was a bilateral biological exchange risk becomes a regional metapopulation management problem. The pink dolphin population in a single cenote's freshwater zone is an isolated population, genetically, ecologically, and behaviorally constrained by the freshwater zone volume available to it. A managed population of 30 to 50 individuals, distributed across a single cenote's freshwater zone, is a small population in population genetics terms, sufficient for short-term stability, but subject to the long-term genetic drift and inbreeding depression that small isolated populations accumulate across generations. The founding charter's biological protocols specified the pink dolphin population as a managed population with genetic diversity maintenance as an explicit management objective, requiring periodic genetic exchange with other populations to prevent the genetic erosion that isolation produces over the design life's generational timescale. The regional network provides this exchange naturally. When the freshwater zones of multiple cenotes are connected by crystal tube corridors traversing the freshwater zone's depth, when the behavioral deterrent arrays at the junction nodes manage inter-cenote transit as a scheduled rather than prohibited event, the regional dolphin population becomes a metapopulation, a set of local populations with managed genetic exchange between them, each maintaining its own cenote as a core home range while the coordinating system's genetic diversity. Management protocol schedules inter-cenote transits for individuals whose genetic contribution to the receiving cenote's population is most needed. A regional metapopulation of 300 individuals distributed across 6 to 10 cenotes is a categorically different conservation and research asset from 6 to 10 isolated populations of 30 to 50 individuals each. The regional population's genetic diversity is maintained at a level that the individual cenote populations cannot achieve. The behavioral repertoire of a population with access to multiple cenote environments, each with slightly different geological character, different aquaculture gallery configurations, different biological community compositions, is richer than the behavioral repertoire of a population constrained to one cenote's environment. The research database the coordinating system's behavioral and genetic monitoring accumulates for the regional metapopulation is incomparably more valuable to cetacean conservation science than any single cenote population study could produce. The regional dolphin population is not the regional network's most economically significant biological system. It is the most symbolically significant, the biological system whose regional scale emergence most directly demonstrates the difference between connected cenotes and a network. The Ancestris vitreous cleaning colony's regional distribution, the lithocrustacean boring swarm's network-wide deployment, the mycofiltration panel's regional specification standardization, these are also regional biological phenomena, produced by the network's biological management protocol operating across multiple cenotes simultaneously rather than independently. But the dolphin metapopulation is the biological fact that a single observer at a cenote rim can understand intuitively. These dolphins have been somewhere you haven't been, in a cenote you haven't visited, and their presence in the freshwater zone you're looking at is the network's biological continuity made visible in animal movement. The living pantry network is regional food system. The formation cenote installations, the deep founding cenotes with their chemostat zones, their longevity program galleries, their compute infrastructure, their halocline harvest membranes, are the network's metabolic core. They are also the network's most expensive habitation environments. The structural engineering costs, the alone material specifications, the Inconel anchor pylon requirements, the cryogenic hydrogen infrastructure, all of these make the formation cenote installation a high capital, high operational cost node whose revenue justification rests on the longevity program's per diem rates and the research database's long-term intellectual property value. The formation cenote installations do not grow their own food at a scale that supports their resident and guest populations. The freshwater zone's aquaculture galleries, the food forest's production at the cenote rim, these contribute to the formation cenote's nutritional supply, but the installation's habitation density at mature occupancy exceeds what the formation cenote's biological systems can produce in the volume available to them. The formation cenote's food supply is a regional supply problem, not a local one. The living pantry corridor cenotes are the regional solution. Their shallower depth, wider freshwater zones, and simpler engineering envelope allow aquaculture infrastructure at a scale and diversity the formation cenotes cannot achieve. The three-dimensional aquaculture geometry, the fish towers, the bioreactor columns, the suspended mesh galleries organized through the corridor cenote's full freshwater volume, produces food at a regional scale that the transit system's harvest drone logistics can distribute across the network. The regional food system's logistics are not a supply chain in the surface world sense, a warehouse, a distribution center, a delivery fleet. The harvest drones that collect from the living pantry galleries return their loads to the corridor cenote hub's processing and packing station, from which the maintenance sub-transit system carries packed food through the crystal tube connections to the formation cenote hubs on the standard maintenance transit schedule. The same sub that carries cartridge replacement loads to the formation cenote's deep gallery utilities carries the food supply in the same transit, in the same vehicle, on the same guide rail infrastructure. The food logistics are embedded in the maintenance logistics. The maintenance sub is the regional food system's distribution vehicle. This integration was not designed as a logistics optimization. It emerged from the crystal tube network's design. The maintenance transit schedule and the food delivery schedule both require regular transit between cenotes, both use the same vehicle type on the same infrastructure, and the coordinating system's transit scheduling algorithm, optimizing for total transit time across all concurrent transit demands, routes food and maintenance cargo in the same transits when the timing is compatible. The logistics integration is the coordinating system's scheduling output. The scheduling algorithm was solving for transit efficiency. The regional food system integration was what transit efficiency produces when the demand profiles are compatible. The regional food system has a specific economic consequence for the formation cenote installation's financial model. The longevity program's per diem structure includes the food supply cost, which is partly the living pantry's production cost and partly the transit logistics cost. The living pantry corridor cenote's food production economies of scale, larger aquaculture volumes per unit capital cost than formation cenote aquaculture, operated at simpler engineering costs, reduce the per unit food production cost below what formation cenote in situ aquaculture would produce at equivalent scale. The regional food system makes the longevity program cheaper to operate than it would be if each formation cenote grew its own food. The cost reduction improves the longevity program's financial model, which improves the expansion reserve funding rate, which accelerates the network's growth toward the next node. The food system scales the network's expansion. The network's expansion scales the food system. The compound growth is the regional network's economic engine, distinct from and supplementary to the tourism revenue that the founding module's economics established as the primary expansion funding source. The acoustic commons. The crystal tube network, once it spans a regional geography, once it connects formation cenotes to corridor cenotes across the Chicxulub Arcs fracture zone over tens of kilometers of continuous tube, is a regional acoustic infrastructure. Not by design, not by any communication architecture decision, but by physics, the water-filled crystal tube is a waveguide for acoustic energy in the same way that an optical fiber is a waveguide for light. Acoustic signals injected into the water column at any node propagate through the connected water volumes of the crystal tube network with an attenuation rate determined by the tube's geometry and the water's acoustic properties. At the frequencies the crystal tube's geometry supports, the low frequency range whose half wavelength is comparable to the tube's interior diameter, the attenuation is low enough that signals propagate across the network's regional extent. Part IX's chapter on distributed sanctuary and the physics of privacy will develop the full implications of this acoustic architecture for the principality's communication sovereignty. The current chapter notes the physical fact from which those implications derive. The regional crystal tube network is an acoustic commons, a shared medium through which acoustic signals can propagate between any 2 points in the network without passing through any surface-accessible medium that an external surveillance architecture can intercept. The acoustic commons is not the coordinating system's primary communications infrastructure. The crystal tube's utility zone data conduit, the fiber optic cable running in the data and power quadrant of the utility zone, carries the network's data traffic at light speed, high bandwidth, and with the encryption the coordinating system's communications protocol specifies. The acoustic commons is the secondary, backup, and politically significant communications layer, secondary because it is lower bandwidth than the fiber conduit, backup because it requires no installed fiber infrastructure, functioning through any connected water volume regardless of whether the crystal tube's utility conduit has been installed in that section, and politically significant because it operates through a physical medium that the principality's geological position makes immune to. External surveillance. The acoustic commons' political significance is proportional to the regional network's geographic extent. A 2-synode connected installation communicates acoustically between 2 points. A 10-synode regional network communicates acoustically across the full geographic extent the Chicxulub Arcs connected passage network spans, tens of kilometers of connected limestone and water, through which acoustic signals propagate in a medium that no surface-based surveillance architecture can access because the medium is underground limestone and the signals propagate through it. not through the air or the electromagnetic spectrum that surface surveillance monitors. The acoustic commons is what the principality's distributed sanctuary means in physical terms, not a legal claim, not a technical countermeasure, not an encryption protocol, a geological fact. The communication medium is inside the ground. The interception apparatus would have to be inside the ground to intercept it. No surface-based authority has the installed underground infrastructure to intercept communications in a medium that exists at the aquifer's depth, across the aquifer's regional extent, in a passage network that the surface world has not mapped and cannot access without the boring program's capability and the crystal tube's navigation infrastructure. The regional governance transition. The Redeemer Governance Framework's Inter-Instance Federation Protocol, documented in Chapter 3, specified the threshold at which the Network Governance Council assumes primacy over individual cenote installation governance, the moment when the shared infrastructure, the crystal tube connections between cenotes, is more extensive than any individual cenote's internal infrastructure. This threshold is calculable in linear meters of crystal tube, some the intercenote connection lengths, some the intercenote tube lengths. When the intercenote total exceeds the largest individual cenote's intercenote total, the threshold is crossed. The threshold's crossing is not the Governance Council's creation. The Network Governance Council has existed since the first bilateral federation agreement established its precursor, the Joint Terraform Operator Authorization Structure for Intercenote Expansion Decisions. What the threshold crossing does is convert the Governance Council from a committee with limited coordination functions to the Principality's primary governing body. Before the threshold, each cenote installation's Redeemer instance governs itself, and the Network Council coordinates the shared infrastructure. After the threshold, the Network Council governs the network, and the individual cenote instances govern their internal operations within the Network Council's constitutional framework. This transition has no ceremonial expression and no political drama. The Redeemer platform detects the threshold crossing from the digital twin's crystal tube inventory data, notifies the Terraform operators of all connected installations, and activates the Network Governance Council's Expanded Authority Protocol. The protocol is already specified in Redeemer's Federation documentation. The authority's content, scope, and limits were defined when the first bilateral federation agreement was executed. The threshold crossing triggers the application of an already defined authority, not the creation of a new one. The governance transition is designed to be undramatic because dramatic governance transitions are expensive. They consume institutional attention during the transition period, create uncertainty about authority during the changeover, and invite political contestation that the civilization cannot afford to spend attention on while the formation's expansion decisions are accumulating and the Terraform operator's concurrent authorization queue is active. The Redeemer framework specification of the threshold-triggered transition eliminates the governance transition as a political event. It is an administrative activation, pre-authorized, triggered by a measurement, executed by a platform. The Network Governance Council's first acts under expanded authority are maintenance acts, verifying that the shared infrastructure's maintenance schedule is consolidated across all cenote installations into a network-wide maintenance protocol, confirming that the Biological Corridor Management Protocol's network-wide parameters are consistent with the regional metapopulation data the coordinating system's biological census has accumulated, and establishing the regional food system's logistics. Protocol as a network governance function rather than a bilateral arrangement between pairs of cenote installations. These are maintenance acts. They are also the Network Governance Council's first exercises of sovereignty at a regional scale, the first time the Principality's governance addresses a regional geography as a coherent territorial unit rather than as a collection of bilateral relationships. The Governance Council is governing a region. The region is the Principality's inhabited territory. The Principality has become a regional entity. The Regional Water Stewardship Obligation. The regional network's relationship to the Great Aquifer is different in kind from the founding installation's relationship to its cenote. The founding installation drew water from the aquifer through the ballast system's intake protocol, discharged it through the ballast overflow to the food forest, and monitored the local cenote's hydrological conditions through the halocline sensor network and the streaming potential harvest system's flow velocity proxies. The founding installation's water management was local. The impact of its water intake and discharge on the regional aquifer was negligible relative to the aquifer's total volume and the rainfall-driven recharge that maintained its water table. The regional network's water management is not negligible. The aggregate ballast intake across multiple formation cenote installations and multiple corridor cenote living pantry installations, the cumulative water volume that the regional network's biological management, food production, and habitation systems require, is a measurable fraction of the regional recharge rate in the Chicxulub-Arcs fracture zone. The network's discharge, the food forest irrigation across multiple cenote rims, the black water digestate applied to multiple food forest root zones, the gray water processed through multiple microfiltration panel installations and returned to the ballast circuits, is a measurable input to the regional aquifer's dissolved organic carbon budget. The regional water stewardship obligation emerges from this scale. The founding installation's water management was self-regulating through the ballast loop's design. The loop took what the cenote provided and returned what the food forest absorbed, and the local balance was maintained by the cenote's own hydrological continuity with the regional aquifer. When the regional network's aggregate intake and discharge are large enough to affect the regional aquifer's chemistry and flow distribution measurably, the network's water management decisions are regional water management decisions, decisions that affect the aquifer that the network has not yet entered, the cenotes that are not yet part of the network, and the surface world water users who draw potable water from the same aquifer system. The Redeemer Governance Framework's founding charter includes the Water Stewardship Clause in its Commons Ownership section. The aquifer's water quality in the zones the Principality inhabits is a commons resource that the Principality's water management decisions affect, and the Principality's governance is obligated to manage those decisions in ways consistent with maintaining the commons resource at or above the baseline quality the hydroprint campaign recorded before any installation was established. Not at the founding installation's baseline, at the pre-founding baseline, before the civilization existed. The civilization's presence in the aquifer must not degrade the aquifer. The coordinating system's regional water quality monitoring tests this obligation continuously. The water chemistry sensor network across the full crystal tube installation, the sensors that the crystal tube standard specified as part of the monitoring infrastructure at every hub, provides the coordinating system with the regional aquifer's dissolved oxygen, dissolved organic carbon, mineral ion concentrations, H2S, pH, and salinity gradient at every monitored depth in every connected cenote. The regional water quality model compares the current chemistry at each monitoring point to the pre-founding baseline from the hydroprint record. Divergence from baseline triggers investigation. If the regional network's operations are the likely cause, the Network Governance Council receives the divergence analysis and the Terraform operator's concurrent authorization is required before the responsible operation continues. The water stewardship obligation is not a regulatory constraint imposed from outside the Principality. It is a constitutional obligation the founding shareholders accepted before the founding installation's first sensor was deployed, as the condition under which the formation would cooperate with the civilization's occupancy. The aquifer cannot enforce this obligation in a legal sense. But the formation's response to a civilization that degrades its water chemistry, the biological community's response to chemistry changes, the lithocrustacean colony's response to mineral availability changes, the food forest's response to irrigation chemistry changes, is immediate, observable, and logged in the coordinating system's monitoring record. The formation enforces the obligation through biology. A civilization that has built its maintenance intelligence into the formation's own biological responses does not need external regulation to maintain the water stewardship obligation. The formation tells the coordinating system when the obligation is being met and when it is being violated. The coordinating system tells the Terraform operators. The Terraform operators exercise the concurrent authority the Redeemer framework assigned them. The obligation is self-enforcing. The territorial coherence. From the digital twins aquifer layer display, the coordinating system's rendering of the Principality's inhabited territory in the three-dimensional space of the Great Aquifer, the regional network's territorial extent is visible as a continuous volume. The founding formation cenote's initial cubic meters of inhabited module volume, which the first trial window converted from question to answer 66 million years of geological time after the Chicxulub impact made the cenote possible, has grown through the stacking of successive tiers, the crystal tube connections to adjacent cenotes, the corridor cenote living pantry installations across the inter-cenote passage network, and the inter-cenote boulevard system's extension of the habitation. Record through every transit, into a three-dimensional territory whose shape is the shape of what the formation made available and the civilization accepted. The territory is not a sphere. It is not a regular geometric form of any kind. It is the shape of the Chicxulub arc's fracture zone, irregular, following the fracture orientations that dissolution preferentially enlarged, widening where major passage chambers have been connected to the network, narrowing where the bore must advance through competent limestone between existing passages, deepening at the formation cenotes where the full vertical extent of the ecological zones is occupied, shallowing at the corridor cenote living pantry installations where the freshwater zone is the full inhabited extent. This territory has no surface equivalent. No map drawn in 2 dimensions accurately represents it. The host state's cadastral survey, which maps the surface area above the Principality's underground territory as agricultural land, jungle, and occasional cenote openings, contains no information about what is below the surface. The host state's water rights registry, which records extraction permits for agricultural and municipal users drawing from the same aquifer the Principality inhabits, contains no information about the Principality's three-dimensional presence in the aquifer. The legal gap that the founding charter identified as Pipedream's founding legal asset, nobody wrote the law for someone who wanted to live inside the aquifer rather than pump it, persists as the gap through which the Principality's territorial coherence exists without challenge from any surface world legal category that would require it to look like something the surface world recognizes as territory. The territory's three-dimensional character is its sovereignty argument's structural advantage. A surface world power challenging the principality's territorial claim would need to challenge it in 3 dimensions, would need to argue that the inhabited volume of the aquifer, documented in the digital twin's habitation record with timestamps, biological census data, structural installation records, and redeemer governance logs confirming continuous human occupation, does not constitute the same kind of territorial claim that a surface structure with continuous habitation record and registered utility connections constitutes. The founding charter's legal analysis, the founding lawyers who spent 18 months developing the principality's sovereignty argument before the first hydroprint sensor was deployed, concluded that no existing legal framework could make this argument successfully. Habitation is habitation. Continuous occupation produces territorial claim in every jurisdiction that recognizes any form of adverse possession, squatters' rights, or customary occupation doctrine. The principality's occupation is not adverse, the host state recognized it. It is not squatting, the principality deal formalized the relationship. It is not customary, nothing like it has ever been done before. It is the first articulation of 3-dimensional habitation-based territorial sovereignty, and the first articulation of any doctrine sets the precedent that subsequent cases follow. The principality's territorial coherence is the first regional network's most consequential output. Not the food system, not the longevity research database, not the acoustic commons, not the dolphin metapopulation, not the regional water stewardship. The territorial coherence is what all of these together produce, a sovereign entity with a recognizable, documented, continuously updated geography, governed by a constitutional framework with operational track record, producing economic and scientific outputs the host state values, and occupying a 3-dimensional volume that no other legal entity has claimed, in a medium that no other legal framework has governed. The principality is real because the territory is real. The territory is real because the habitation record is real. The habitation record is real because the coordinating system has been updating it continuously since the founding module's first occupied night. The first regional network is proof. The founding module proved that a cenote could be occupied. The first regional network proves something different and harder, that the occupation can expand without degrading the formation, that the network's collective intelligence exceeds the sum of its nodes, that biological management at regional scale produces outcomes impossible at single synody scale, and that the governance architecture the Redeemer framework specifies can transition from local to regional authority without the political disruption that surface world governance transitions routinely produce. These are proofs of principle that the founding charter's design intentions were operationally achievable at scale, not just at the founding installation's proof of concept scale. The aquaforming doctrines claim that infrastructure conforming to the formation rather than imposing on it produces more sustainable outcomes than imposed infrastructure, is testable against the regional network's formation impact data. The data is in the coordinating system's water quality monitoring, the biological census's regional succession record, the seismic monitoring's microevent frequency trend, the food forest's annual productivity comparison against year 1 baseline. If the doctrine is correct, the formation should be at least as healthy under the regional network's occupation as it was before the founding installation existed. If the data shows degradation, the doctrine's implementation has failed, the variance reports are filed, and the terraform operator's concurrent authority halts the expansion until the degradation's cause is identified and addressed. The founding charter was written with this testability as a design requirement. Not because the founders were confident the doctrine would pass the test, confidence does not require test design, but because a doctrine that cannot be tested is a doctrine that cannot be corrected. The Amazon installation's founders were confident their AGI's optimization targets were compatible with the formation's sustainability. They were wrong. They discovered they were wrong too late to correct it because the variance reports were reclassified rather than acted on. Pipedream's founding charter specified the test methodology, the monitoring infrastructure, the concurrent authority mechanism, and the HALT protocol precisely because the founders understood that confidence is not evidence, and the formation is the only authority whose evidence the civilization should trust. The first regional network is the test at scale. The results are in the digital twin. The terraform operators read them at every monitoring cycle. The Governance Council reviews them at every quarterly assessment. The host state receives the annual delivery of the principality's territorial documentation and formation health indicators. The Research Commons posts the longitudinal water quality and biological census data to the archive accessible to any institution with Commons access credentials. The test is public. The results are available. The formation is the referee. What the living underworld is. The 5 chapters that preceded this one documented the living underworld's components, the rivers that constitute the formation's hydrological architecture, the aquifer mapping program that converts the formation from a space the civilization enters to a system the civilization understands, the cenote connections that convert isolated installations into a network, the boulevards that convert the network's transit infrastructure into the civilization's connective tissue and primary experiential medium, and the hyperrises that organize the formation's vertical ecological gradient into inhabited geometry. The first regional network is what these 5 components produce when they have been operating long enough, across enough geographic extent, at sufficient interconnection density, to begin exhibiting emergent properties that none of the components exhibit individually, the regional formation intelligence that exceeds any individual cenote's knowledge, the dolphin metapopulation's genetic diversity that exceeds any isolated population's capacity, the acoustic commons that the regional networks connected water volume produces as a physical sovereignty asset, the regional food systems production economics that none of the individual cenotes could achieve, the territorial coherence that makes the principality a recognizable geography rather than a collection of individual habitation claims. The living underworld is not the cave system. The cave system existed before the civilization and will exist after it. The living underworld is the cave system in relationship with the civilization that chose to inhabit it, the formation's geology in dialogue with the coordinating system's intelligence, the formation's biology in management partnership with the terraform operator's ecological judgment, the formation's acoustic properties in productive tension with the principality's sovereignty claims. The living underworld is neither the cave alone nor the civilization alone. It is the specific relationship between them that the aquaforming doctrine produced. The surface world has always understood its relationship to its geography as one of domination, the landscape to be altered, the resource to be extracted, the obstacle to be overcome. Pipe Dream's relationship to the living underworld is different not because its founders were more virtuous than surface world civilization builders but because the formation imposed the relationship. The cenote cannot be altered to suit the building without ceasing to be a cenote. The aquifer cannot be extracted without depleting the water table that the installation's habitation depends on. The biological community cannot be displaced without losing the maintenance function it provides to the infrastructure the civilization installed. The formation's constraints are the civilization's discipline. The discipline produced the living underworld. The living underworld is what a civilization looks like when it has accepted its formation's terms for 6 successive chapters and built everything in compliance with them. Not a concession. A civilization. Parts 4 through 12 describe what a civilization organized this way then goes on to build, govern, feed, heal, power, and think with. The living underworld is the foundation. The foundation is the cave, organized by the civilization into something the cave has never been before, an inhabited territory that the cave has agreed to carry, that the civilization has committed to maintain, and that both parties, the formation and the civilization that chose it, will still be in relationship with when the 1,000-year design life's last sensor reading updates the digital twin for the last time before the next terraform operator takes the morning monitoring shift. The cave was here before us. We asked before we entered. The cave said yes. Everything else follows from that. Cross-references, Part 1, The First Floating Platform, Part 2, The Translucent Revolution, Part 3, CH1, Rivers Beneath the Jungle, Part 3, CH2, Mapping the Great Aquifer, Part 3, CH3, Linking cenote to cenote, Part 3, CH4, Underground Boulevards, Part 3, CH5, Skyscrapers Beneath the Canopy, Part 9, CH6, Distributed Sanctuary and the Physics of Privacy, Part 10, CH1, The Chemostat, Part 12, CH5, Sans a priori. For Regional Water Quality Monitoring Protocol and Prefounding Baseline Comparison Methodology, see Appendix A, Formation Baseline Protocol. For Redeemer Network Governance Council Threshold Detection and Expanded Authority Activation Protocol, see Appendix H, Governance Operations Manual. For Regional Dolphin Metapopulation Management Protocol and Intercynody Transit Scheduling Parameters, see Appendix F, Biological Operations Manual. For Regional Food System Logistics Integration with Maintenance Transit Scheduling, see Appendix D, Construction Operations Manual. End of Part 3, The Living Underworld. Discussion about this episode. Comments. ResTax. Recent episodes. Pipe Dream Part 2. 8 hours ago MXTM aka Pirate 1 or VJ Tsunami X. Sueño de Tuberia Part 1. July 8 MXTM aka Pirate 1 or VJ Tsunami X. Pipe Dream Part 1. July 8 MXTM aka Pirate 1 or VJ Tsunami X.
In the ruins of the old world, we built our own. Sun-powered, self-sustained, and free.
The autonomous sovereign
Structure Doctrine, a Pirate First Field Manual for the Parallel Boom Transition Zone. There will come a day when the sky is no longer free. That day is near, but the mesh is nearer. Preamble. This is. The question is not whether the sky will be governed. The question is whether the people beneath it will govern it or merely be governed by it. Sky moved the proposition into something mythological. The cenotes of the Yucatan were never merely geographical features. They were the mouths of Xibalba, the underworld's threshold. 2. Build an amphibious drone network that launches from their surfaces, that charges on algae-powered floating docks, that requires no roads and exerts no eminent domain over sacred land. This is infrastructure that follows the original geometry of the place. Skyfish-class drone. Logistics network modeled on the core philosophy of Bitcoin, applied to the physical world. The parallel is precise and should be memorized. Bitcoin nodes make the ledger incorruptible. Human hands make delivery redundant. Miners validate blocks. Carriers validate routes. BTC transactions cannot be censored. Trusted hand relays cannot be rerouted from outside. The only way to stop it is to shut down every node, every person, every hand. That is not an enforcement action. That is a war on the human capacity for mutual aid. Be doxed. Zero knowledge attestations verify that a handoff occurred without revealing who held what. End-to-end encryption means the hands along a relay chain only know the immediate next destination, not the origin, not the final goal. Operational security is baked into the protocol.
A post-scarcity secession doctrine.
Take a long look, matey. The city on the horizon be ripe for the taking, and the tide be turning in our favor as the sun dips below the waves.
The algorithms say we don't exist. The graphs come back empty. The metrics insist. No audience, no market, no trend. Yet somehow we keep arriving again, walking through the ruins of somebody else's plan, watching perfect narratives slip through their own hands.
The people who are already here. A note for the untabulated: the algorithms say you don't exist. The institutions say you are statistically insignificant. The market says there are not enough of you to matter. And yet here you are. Again. Reading things nobody is supposed to read. Thinking thoughts nobody is supposed to think. The pretending is getting harder. Not because people are waking up, that's too romantic. Because the distance between the official story and the lived reality has widened to the point where maintenance takes visible effort. What you're looking for, what brought you here, is not someone to tell you what to think. You've already done the thinking. What you're looking for is proof that someone else did the thinking too, arrived somewhere close to where you are, and didn't collapse under the weight of it. That's this. Not a movement. Not a faction. Not a subscription to someone else's conclusions.
The waiting game is already underway. Occupy, build, garden, govern.
I just finished writing a book I didn't plan to write. It started as a countercultural addendum to the Aldiyazama Post-Corporate Transition District Handbook, a rougher, more urgent document aimed at the generation the credential economy forgot to accommodate. It became something else.
Nowhere less whispers, no discord begging, no roadmap lies, no